Hi friends, welcome to our YouTube channel Naraj Academy. The main aim of this lecture is to discuss about the electric circuits formulas in a very detailed manner. So these formulas are very much useful for the IAS exam and also GATE and some of the state exams also these formulas will be very much useful. So we are going to study about the first basic concept, which is the average and the RMS value of the signals. So now we are going to see some of the basic signals and also what is the value of the average value and also the RMS value we are going to learn now. So therefore you can see clearly this is called as a sinusoidal signal. Let me assume that basically all the signals are periodic in nature. So as it is a sinusoidal signal with a peak value of Vm, then this is called as the half of the time period and this is the full time period. So then the average value will be 2Vm by pi. See, for any signal symmetric with respect to the y-axis, always we have to choose only half of the time period, because if you take the full time period, its average value will be 0 because this is a positive area and this is a negative area. So therefore, in the overall time period, it is going to become 0. That is the reason if a signal is symmetric, then we are going to choose only half of the time period, and for that reason only we are going to find what is the value of the average. So if you do in that manner, we are going to get the average value of the pure sinusoidal signal is 2Vm by pi, whereas the RMS value of the pure sinusoidal signal is Vm by root 2. Suppose if you take a full wave rectified signal, so it is going to have only positive nature, then you can see clearly here the signal is going to have average value same as the previous value, which is 2Vm by pi, and also its RMS value is also same as the previous signal, which is Vm by root 2. So RMS value and the average value of this full wave rectified signal is same as the pure sinusoidal signal also, it is both are same. So now suppose if the signal is a half wave rectified signal, means only for the positive region the signal is going to present, but for the negative region the signal is absent. Then what is the average value and the RMS value of this signal, which is half of the previous value, which is we can say V average is equal to Vm by pi, whereas Vrms is equal to Vm by 2. Means for the above signal, see, for the above signal we are going to keep half of the portion. So therefore average value is half of the previous value, whereas Vrms is equal to 1 by root 2 times of the previous value. So therefore we can say clearly V average is equal to Vm by pi, whereas Vrms is equal to Vm by 2. So if any signal is half of the period signal, means if any signal is half of the previous signal, then we can say that here the average value is half of the old value and the RMS value will be 1 by root 2 times the old value. Suppose there is a square signal with the positive of Vm and negative of Vm, so therefore minus Vm. So we can say here the average value will be is equal to Vm, because we are going to take only for the positive half cycle but not for the negative half cycle, and also the RMS value is equal to Vm. So average value is equal to Vm and also the RMS value is equal to Vm for a pure square wave signal. Whereas if you are going to clip half of the portion, means if you are going to clip the negative part, then we are going to get a half wave rectified signal. So for this the average value will be Vm by 2. I have already told you, if you are going to clip some of the signal, previous signal, so therefore the new average value will be half of the previous value, and the Vrms will be 1 by root 2 times of the previous value signal, which is Vm. So therefore we can say V average is equal to Vm by 2, whereas Vrms is equal to Vm by root 2. Suppose if you are going to take this ramp signal in this manner with a period of pi, then we can say clearly the average value is equal to Vm by 2. So if you want to know what is the average value, just find the area of this signal by the time period. So area is nothing but half into pi into Vm by pi. So therefore you are going to get Vm by 2. If you want RMS value, which is Vm by root 3. So we can say for ramp signal or triangular signal which is of periodic nature, the average value will be Vm by 2, whereas Vrms is equal to Vm by root 3. So for a triangular signal or the ramp signal of periodic nature, then we can say V average is equal to Vm by 2, whereas Vrms is equal to Vm by root 3. Suppose it's a pure triangular signal, you can see clearly here it is going to have a peak of p pi and it is going to have a period of 2 pi. It's also a periodic signal. Then the average value and the RMS value of the ramp periodic signal and the signal is same. So therefore we can say the average value is equal to Vm by 2 and the Vrms is equal to Vm by root 3. So both are going to have the same nature. So therefore we can say V average is equal to Vm by 2 and Vrms is equal to Vm by root 3. Suppose if you are going to clip this off, so therefore we can say the new average value will be half of the previous value, which is 1 by 2 into Vm by 2, it is nothing but Vm by 4. And if you want the RMS value, which is 1 by root 2 times the RMS value of the previous signal, which is Vm by root 2, 1 by root 2 into Vm by root 3, which is Vm by root 6. Suppose if you are going to take a constant signal, then the average value and the RMS value are equal to the peak value of the signal, which is Vm. So therefore we can say Vrms is equal to Vm and Vrh is equal to Vm. So these are some of the important signals, and I have discussed about the what is the average value and also the RMS value of the signal. So now we are going to discuss about some of the sources which are important in the electric circuits. So the first type of source is the ideal voltage source. So for ideal voltage source, the diagram will be in this manner. So you can see clearly this is a ideal voltage source. For ideal voltage source, there will be no internal resistance. So this is Vs, and we are going to connect a load. It is of variable nature. So I am going to assume the load voltage is VL and the load current is I. And also, as there is no other branch, we can say the source current is equal to load current, and also there is no internal resistance drop. So by KVL also we can say that the source voltage is equal to load voltage, which is Vs is equal to VL or VL is equal to Vs. Then I want to draw what is the diagram with respect to VL and I. See, no matter whatever the load, always the current is going to get changed, but definitely the load voltage is always equal to source voltage. See, no matter whatever the current, if the current is a positive or if the current is negative, still VL is equal to Vs always. So we are going to get in this nature. So therefore we can say, irrespective of the current drawn by the source, irrespective of the current drawn by the load, always the load voltage is equal to source voltage. This we are going to call it as the ideal voltage source. So for practical voltage sources, there will be a small amount of internal resistance. So if you are going to include a small amount of internal resistance, then we are going to say it as the practical voltage source. So therefore now we can say here we are going to connect some load to a practical voltage source. So this is a practical voltage source and this is a load. So we are going to connect the load to the practical voltage source. Then we can say the load is going to draw some amount of current. I am going to represent with the symbol of I. Then the load voltage is VL. So by using the KVL, we can say that here the load voltage is equal to source voltage minus I into Rs. So with the help of KVL, we can write this expression, which is VL is equal to source voltage minus I into Rs. So you can see clearly as the current is going to get increased. As the current increases, this factor increases, so overall factor will decrease. So therefore we can say when I is equal to 0, then only VL is equal to Vs. Otherwise, we can say clearly that VL is going to get decreased as the current value is increases. So we are going to get a graph in this nature, which is as the current increases, the VL is going to get decreased in this straight line format. So when current is equal to 0, VL is equal to Vs. But the current is going to get increased, so therefore VL is going to get decreased. So this is the meaning of this graph. So therefore we can say only for ideal voltage source, VL is equal to Vs. But for practical voltage source, always there will be small amount of internal voltage drop. So because of that only, the load voltage is going to get decreased whenever the current is very, very high. So now we are going to learn about the ideal current source. So here this is a diagram of the ideal current source. Means here this ideal current source, and we are going to connect some load to this ideal current source. So this is going to draw some amount of current I, and the load voltage is equal to VL. So you can see clearly in KCL, the incoming current should be equal to outgoing current. So therefore I should be always equal to IS. So if you are going to draw the diagram with respect to VL and I, you can see I is equal to IS. Irrespective of the voltage VL, whether VL is a positive or negative, always current I is equal to IS. So therefore the load current will be always equal to source current irrespective of the load voltage. Whether the load voltage can be either positive or negative, always I is equal to IS. So you are going to get a graph in this nature. Because for our ideal current source, the internal resistance is very, very infinity. So because of that reason only we can say that current I, the load current is equal to source current. So now we are going to discuss about the practical current source. So for practical current source, there will be a small amount of, so we are going to represent in terms of parallel manner, which is RS, and is the source current IS. So this is called as the practical current source diagram. So now we are going to connect a load across this practical current source. So let me assume the current I is called as the load current drawn by the load, and VL is the load voltage across the load. So now by using KCL we can write, which is the current I is equal to source current minus VL by RS. So therefore this equation we are going to get if we apply the KCL across this node. So therefore load current is equal to source current minus VL by RS. So you can see clearly when VL is equal to 0, then only the load current is equal to source current. But if the load voltage is going to get increased, means this value increases, so overall value will decrease. So you can see clearly whenever the VL increases, the value of the load current goes on decreases. So you can see clearly from this, the graph is nothing but it's a straight line. So therefore we can say clearly that whenever the load voltage increases, the current across the load is going to get decrease. So now we are going to learn about the dependent sources. See, dependent sources means the value of the source, that means the quantity of the source is going to depend upon some other parameter. So we can say the type of sources are said to be dependent sources. So here there are 4 types of dependent sources, which are the voltage control voltage source, current control voltage source, voltage control current source, current control current source. So you can see clearly here voltage control voltage source means the voltage is going to control this voltage source. So we are going to represent the dependent sources with the help of this rhombus diagram. So therefore as it is a plus minus, so we can say K into V1 means V1 is called as a voltage control variable. This is going to control this voltage source. So because of that reason we can say voltage control voltage source. Similarly here current control current source means current is going to control the quantity of this voltage source. So because of that reason only we can say it is a current control voltage source. So I1 is a current control parameter. This is going to control the voltage across this circuit, across this symbol. So therefore we can say it's a current control voltage source. Similarly here V2 is the voltage variable. It is going to control the current source across this one. So therefore we can say voltage control current source. Similarly here it is a current variable, so it is going to control the current in this source. Because of that reason only we can say it is a current control current source. So simply voltage control voltage source, current control voltage source, voltage control current source, and current control current source. So these are the 4 types of dependent sources which are going to present in the electric circuits. So now we are going to learn about the series connection. Series connection means the current in both the elements should be same. Then only we can say that this is said to be a series connection, means the current in the Z1 is equal to current in the Z2. Then only we can say it is a series combination. So let me assume the voltage source is going to apply across these two elements. So therefore the voltage drop across the element Z1 is V1 and the voltage drop across the element Z2 is V2. So now we can say that I want to make this circuit into equivalent in this manner. So see, overall this combination is going to become a very simple circuit. Then what is the value of the Z equivalent we need to figure out. So therefore we can say clearly that Z equivalent is equal to sum of the individual impedance, which is Z equivalent is equal to Z1 plus Z2, whereas V1 is equal to by voltage division principle, which is supply voltage into voltage across that impedance by sum of the overall impedances. So therefore V1 is equal to V into Z1 by Z1 plus Z2. Similarly V2 is equal to supply voltage into voltage across that impedance by sum of the impedances. So therefore V2 is equal to V into Z2 by Z1 plus Z2. So this is for a general format. Now we are going to apply this principle for the resistive network, inductive network, and also for the capacitive networks. So when two resistors are connected in series, then the equivalent resistance is equal to sum of the individual resistance, which is R1 plus R2. Then V1 is equal to the voltage drop across the R1 resistance is equal to supply voltage into R1 by R1 plus R2. Similarly V2 is equal to supply voltage into R2 by R1 plus R2. Similarly, there is an inductive network, means whenever we are going to connect two inductive elements in a series manner, then the net equivalent inductance is equal to sum of the individual inductance, which is L1 plus L2. So whereas V1 is equal to the voltage drop across the first inductor is equal to V1 is equal to V into L1 by L1 plus L2, whereas the voltage drop across the second inductor is equal to V2 is equal to V into L2 by L1 plus L2. So the format of this is same as the previous resistive network. So now we are going to learn about the whenever the two capacitors are connected in series, then what is the net equivalent capacitance, which is C equivalent is equal to C1 C2 by C1 plus C2. So this is called as the net equivalent capacitance, whereas V1 is equal to supply voltage into C2 by C1 plus C2, whereas V2 is equal to V into C1 by C1 plus C2. And also, if you do the division of these two things, just V1 by V2 is equal to C2 by C1, or simply we can say V1 into C1 is equal to V1 into C1 is equal to V2 into C2, or simply we can say the charge is equal to same, so Q is equal to C into V, so therefore C1 into V1 is equal to C2 into V2. So this is a very easy way to remember also. So by these are the some of the, for whenever the two elements are connected in series, then we learn the formulas for the equivalent impedance, and also the voltage drop across the first element and the voltage drop across the second element, and also we learn what is the value of the simple circuit combination. Also we have learned for resistor, inductive, and also for the capacitor. Suppose when two elements are connected in parallel manner, then suppose these are the two elements Z1 and Z2 are going to connect in parallel manner across a voltage source. So the two elements are connected in parallel means the voltage across them two elements is same. Then only we can say these two elements are said to be in parallel. So the total current drawn by this overall impedance is I1, but because of the branches, let me assume the current in the Z1 is I1 and the current in the Z2 is I2. So now I want to do the simplification of this circuit into a very simple circuit, which is Z equivalent. So this Z equivalent should also draw the same amount of current, or simply we can say the power consumed by the Z1 plus Z2 should be equal to the power consumed by the Z equivalent. So therefore we can say Z equivalent is equal to Z1 into Z2 by Z1 plus Z2. So if you want to know what is the value of the current I1, which is I into Z2 by Z1 plus Z2, or simply we can say I into 1 by Z1 by 1 by Z1 plus 1 by Z2. So this is the only, you can apply only whenever the two branches are in parallel, but this formula you can apply for any number of branches in parallel. So therefore this is a very easy way to remember this one also. So similarly I2 is equal to I into Z1 by Z1 plus Z2 is equal to I into 1 by Z2 by 1 by Z1 plus 1 by Z2. So this we are going to call it as the current division principle. So if you want the current across Z1, which is supply current into opposite impedance by sum of the impedance, or you can say in another formula, which is I into I1 is equal to I into supply current into reciprocal of this impedance by sum of the reciprocal of the all the impedance. So in that fashion also you can apply, still you are going to get the same result. See, this formula you can apply for any number of parallel branches, but you can apply only this formula only when the two branches are there, but not more than that. Suppose when the two resistors are connected in parallel, then the net equivalent resistance is equal to R1 into R2 by R1 plus R2, whereas current I1 is equal to I into R2 by R1 plus R2, whereas I2 is equal to I into R1 by R1 plus R2. So if two inductance are connected in parallel, then the net equivalent inductance is equal to L1 into L2 by L1 plus L2, and similarly I1 is equal to I into L2 by L1 plus L2, and similarly I2 is equal to I into L1 by L1 plus L2. Suppose if you are going to consider the capacitance network, means whenever the two capacitors are connected in parallel, then the C equivalent is equal to sum of the individual capacitance, which is C1 plus C2, and here I1 is equal to I into C1 by C1 plus C2, and I2 is equal to I into C2 by C1 plus C2. It's a very easy way, or you can say it is a reverse of this R1 and R2, and R1 and it is a reciprocal of the resistance and the inductance. So if you do I1 by I2, we are going to get C1 by C2. So now we are going to discuss about the source transformations. Source transformations means we are going to convert this practical voltage source into a practical current source. Then what is the equivalence between them? See, you can replace this practical voltage source by practical current source, means the load connected across the terminals A and B are going to absorb the same amount of power, no matter whether you replace this by this or this by this. That is the meaning of the equivalence, means the load connected across the terminals should always consume the same power when we are going to replace either of these one in order to simplify the circuit. So let me assume this is the voltage Vs and this is the current RS. So we are going to convert this practical voltage source into practical current source. So if you know one parameter, then how to figure out the remaining things we are going to see. So therefore, here the open circuit voltage is equal to Vs, and here also the open circuit voltage should be always equal to Vs. Means the current, it is open circuit, means the current here is 0. So whatever the supply current should go through this RS also. So therefore voltage is equal to Is into RS. So therefore Vs is equal to same, it should be here also. So therefore Vs is equal to Is into RS. And the resistance across this, if you short circuit this one, we are going to get the resistance across the A and B terminals is RS. And really, if you want the resistance across the terminals A and B, you have to open circuit the current source. So therefore here also the net resistance is RS. So we can say simply that here Vs is equal to Is into RS, and it is connected in series. Here we have to replace in parallel for current source. This is the only difference. And here you can see clearly, here there is a positive symbol and here is a negative symbol. So arrowhead should be always in the positive and the tail should be in the negative direction. So therefore this is the direction of the current. Always for a positive, the arrow should be in the positive direction, whereas the tail should be at the negative direction. So therefore this is called as the negative symbol and the positive symbol. Always arrow at the positive symbol and the tail at the negative. So this is a way to convert the practical voltage source into a practical current source, or either you can convert from practical current source to a practical voltage source. So by this we can do the simplification of any complex circuits in a very easier manner, and we can get whatever the results that we really want to solve the numericals. So now we are going to see the transformations from star to delta and delta to star. So up to now we have learned how to convert a practical voltage source to practical current source, or practical current source to a practical voltage source. So now we are going to convert how the loads we can convert from star connection to a delta connection. So this is called as the star connection and this is called as the delta connection. So let me assume the delta elements are Z1, Z2 and Z3, and the star elements are ZA, ZB and ZC. So normally any impedance for resistor we have to replace Z by R, for inductor we are going to replace by J omega L, for capacitor we are going to replace by minus J by omega C or 1 by J omega C. You can go for any of the formats, still you are going to get the same result. But suppose if you want to convert from star to delta, means if you know the value of star values, how to get the delta values, means if you want this Z1, then this Z1 is connected to the ZA and ZB. So you have to add these two elements, which is ZA plus ZB plus, and do the product of this impedance, which is ZA into ZB by the opposite impedance is ZC. Similarly, Z2 is equal to ZC plus ZB plus ZC into ZB by ZA. Similarly, Z3 is equal to ZA plus ZC plus ZA into ZC by ZB. So simple format is whatever this element is connected to, that values you should add, plus again product of those elements by the divided by the remaining element. So this is the way you have to convert a star network into a delta network. But vice versa, how to connect a, suppose if you know the delta elements, how to convert into star fashion, which is if you know Z1, Z2, Z3, how to get the value of ZA, ZB, ZC, which is ZA is equal to, see this ZA is connected to Z3 and Z1, so therefore do the product of these elements, which is Z1 into Z3 by summation of all the delta elements, which is Z1 plus Z2 plus Z3. Similarly, ZB is equal to Z1 into Z2 by Z1 plus Z2 plus Z3. Similarly, ZC is equal to Z2 into Z3 by Z1 plus Z2 plus Z3. So this is the way that we have to convert from star to delta and delta to star. So this is we are going to do in order to simplify the circuit. So for resistor replace Z by R, for inductor replace Z is equal to J omega L, and for capacitor replace Z is equal to minus J by omega C or 1 by J omega C. So now we are going to learn about the mesh analysis. See, there are certain methods to simplify the circuit. So in order to simplify any complex circuit, we are going to do some procedure in order to do the calculations of any parameter you want in a given circuit. So the first one is the mesh analysis. Identify total number of meshes in a given circuit. See, meshes is not always a loop, but meshes can be a loop, but every loop cannot be a mesh. So listen carefully, every mesh is a loop, but every loop is not a mesh. Means inside a meshes there will be no other loops, but inside a loop there may be other loops or meshes. So because of that reason only we can say every mesh is a loop, but every loop may not be a mesh. So first identify total number of meshes in a given circuit. Assign the current direction for each mesh. Develop KVL equation for each mesh. By solving KVL equations, find the loop currents and then figure out the branch currents. So in the mesh analysis, the first thing is you have to figure out how many meshes are there in a given circuit and assign the current direction either clockwise or anti-clockwise up to you. And then what you have to do is you have to apply the KVL equations. And the number of meshes is equal to the number of KVL equations. As the number of KVL equations is equal to number of unknown parameters. So you can solve all those things and you can get the loop currents. So with the help of this loop currents, you can figure out the value of the branch currents also. So this is the procedure. You should always go for the mesh analysis. So the next method in the electric circuits, which is the nodal analysis. See, in the nodal analysis, identify total number of principal nodes. Principal nodes means at least means if there is more greater than or equal to 3 number of branches. If at any node means if 3 or more branches, are going to meet at a certain point, then we are going to call that point as the principal node. So therefore, we have to find. So first thing is you need to identify how many number of principal nodes are going to present in the given circuit. After identifying principal nodes, take one node as a reference node. So therefore, here after identifying the principal nodes, you can take any one node as a reference node, or we can say we are going to assume it as a zero potential. So therefore, then assign the voltage at each node with respect to reference node, and the reference node voltage is always equal to 0. So see, after assuming one principal node as a reference node, then the remaining nodes voltages you need to mark it with respect to the reference node, and the reference node voltage is 0. And develop KCL equations at each non-reference node, and by solving KCL equations, find node voltages and then branch currents. So then what you have to do is, then you have to apply the KCL at each and every remaining reference nodes, and then the number of reference node is equal to the number of KCL equations you are going to get, and then you can solve all these equations to get the node voltages, and with the help of these things you can figure out whatever the things that you get, like branch currents also you can easily figure it out. So this we are going to say it as the simply nodal analysis method. So in the nodal analysis method, the first thing is you need to identify how many number of principal nodes are going to present. So out of that one principal node, you are going to assume it as a zero potential or reference node, and you have to mark the remaining reference node voltages as some values with respect to the reference node, with respect to the ground potential, and then by using the KCL at each and other non-reference nodes as the principal nodes as, then we have to apply KCL then, and across them we are going to get equations, and you have to solve them to get the node voltages, and with the help of these things you can figure out the whatever the parameter you want, like branch currents. So now we are going to learn about the superposition theorem and the homogeneity principle. In a linear network with several independent sources acting simultaneously, the response in a particular branch is the algebraic sum of the individual response calculated by treating only one independent source at a time. So here we see the point is very simple. Suppose if you take any linear network, suppose there are several independent sources are going to present simultaneously, means at each and means at every time every source are going to get present. Then the response in the particular branch is the algebraic sum of the individual response calculated by treating only one independent source at a time. So therefore, see, suppose in a linear network there are so many independent sources like voltage sources and the current sources. There are only independent voltage source and the independent current source. Then the response in any branch is equal to the algebraic sum of the responses due to only one source at a time. So therefore, only one source is going to act at a time. Then we can say if you have to add the each and every response, then you have to get the overall response when all the things are going to act simultaneously. So suppose if you are going to consider one voltage source, means the remaining voltage source and the remaining current source should be 0. So voltage source 0 means you should short circuit, and the current source 0 means you have to open circuit. This is the fashion you should consider in order to figure out the response due to each voltage source and the current source, and then we have to add all these values to get the overall response when all the sources are going to act simultaneously. See, the sources are only independent voltage source and the independent current source. In a linear network with only one independent source in a circuit, then if the excitation is multiplied by constant K, then the response in all the branches are also multiplied by k. Suppose you take any linear network and there is only, the special condition is there is only one independent voltage source, whether it can be current or whether it can be voltage. And if you are going to increase this parameter by some amount of k, or increase this value by some parameter k, then the overall response in any branch is going to increase by the same amount of factor. So when the input is increased by k, the output is also going to increase by same value of k. So we are going to call it as the homogeneity. So this is called as the homogeneity and this is called as the superposition. So therefore overall response is equal to summation of each and every response. And homogeneity means if you are going to improve the input by, if you are going to increase the input by small amount of quantity, and by the same small amount of quantity also, the output is also going to get changed. So this we are going to call it as the homogeneity principle. So now we are going to learn about the Thevenin theorem and the Norton theorem. Suppose you take any linear complex circuit. So this is a very linear complex circuit. It is going to have the two terminals A and B. Then we can simplify this complex circuit into a very simple circuit of practical voltage source or practical current source. So you can get all this linear complex circuit into a very practical voltage source or practical current source. You can make this as a simplified version. So if you know, I already told you the conversion between the practical voltage source to a practical current source, which is here VTH is equal to IN into RTH, and also RTH and RTH are both are same. So therefore, see, listen carefully, VTH is equal to IN into RTH, and also here the Norton current is also called as the short circuit current. See how to get the value of the VTH, I will explain now. See here, what you have to do is, for A and B, to figure out the value of the VTH, just bring some voltmeter and keep across the terminals A and B. So whatever the reading which is measured by this voltmeter is called as the Thevenin voltage. And if you want to know what is the value of RTH, then here keep some ohm meter across the terminals A and B. But before that, we have to remove all the sources in this circuit. Means we have to short circuit the voltage, ideal voltage source, and open circuit the ideal current source. Then whatever the resistance you are going to get across A and B, that we are going to call as the RTH. Same thing as here also RTH. But here the way to find the value of Rn is just take some one small ammeter and keep it across the A and B terminals. Means you directly short circuit the terminals A and B, then the current flown by this ammeter, from this ammeter we are going to call it as the short circuit current or the Norton current. So by this way we can figure out the value of the VTH and the IN and also RTH. So VTH is called as the open circuit voltage measured between the A and B, and RTH is called as the equivalent resistance measured between the A and B. So I have told you how to figure out these values also, I have just now explained. When a network with all our independent sources, then we will find, suppose if you take some complex circuit, so in that circuit we are going to have only all the independent sources are going to present. Means there is nothing like dependent sources, everything is a independent source are going to present. Then we can easily find the VTH. See, we can easily find the value of the VTH, and also we can easily find the value of ISC or short circuit current or the Norton current. So VTH means just take the voltmeter across the terminals A and B and you can find the value of VTH. If you want short circuit current means just do the short circuit of the terminal A and B and find the value of the current flowing through terminals A and B. That is called the short circuit. But if you want the Thevenin resistance, just do the division of the Thevenin current by the Norton current, which is VTH by ISC. Or you can go by the external source method also we can do. The external source method is very simple, which is external source method means just, I told you, first remove all the independent sources, the short circuit the ideal voltage source and open circuit the ideal current source, and keep here some external source and find out what is the amount of current flowing through this source. So Thevenin resistance is equal to voltage by current. So what is the external voltage by the current which is injected into the circuit. So if you do the division of these two things, you are going to get the value of the RTH. So this is called as the external source method. So we can get the value of VTH, we can get the value of ISC. So RTH we can figure out by two methods, which is the VTH by ISC or external source method. Suppose when a network with at least one independent source and at least one dependent source, then what is going to happen? Suppose if you take any complex circuit, in that there is at least one independent source and also at least one dependent source, then we can find VTH. VTH means just take the voltmeter across the terminal A and B, and you will get the value of VTH. And if you want ISC or Norton current, just do the short circuit across the terminal A and B, then find the value of the current through these terminals, then we are going to get the value of ISC. Similarly, RTH also we can find with the help of VTH by ISC or by external source method. So these both are same. So this, for these two cases, everything is same. Means we know the value of VTH, we know the value of ISC, just do the division, or with the help of external source method also we can get the value of RTH. So this is the way that we can get with the help of these two methods. When a network with no independent sources but at least one dependent sources, means, see here, suppose in the circuit there are no independent sources, means there are only dependent sources, means that circuit is fully of dependent sources, means at least one is the dependent sources, then these circuits are called as the dead circuits, because there is no ideal voltage source or no ideal currents. So we can say simply this circuit is said to be a dead circuit. So now VTH is equal to 0 volt, because if you keep any voltmeter, as there is no independent voltage source, so definitely the voltage equal to terminal A and B is 0, and similarly the Norton current or the short circuit current is also equal to 0, because there is nothing like independent voltage source. Because of them only the current is going to get flow. If they are not there, means definitely VTH is equal to 0 and ISC is equal to 0. But now RTH is not equal to VTH by ISC, because we can't find with the help of VTH by ISC, but there is only one method, which is ESM, external source method. Only by this method only we can find the value of RTH, but not by the first method, which is VTH by ISC. So I can say, I am clearly saying that VTH is equal to 0 and ISC is equal to 0, but RTH we can only find with the help of the external source method. So RTH, by using only external source method only, we can find the value of the RTH, means keep some external voltage source and figure out the amount of current which is injected into the circuit, then do the ratio of these things, we are going to get the value of the RTH. So we have learned about the three methods, or we can say three circuits. Only independent voltage, so independent source are going to present, or at least one independent source, or at least one dependent source. The last one is only dependent source are going to present, means there is nothing like independent sources. Then we have figured out the three cases also, we have learned in a very detailed manner. So now we are going to learn about the maximum power transfer theorem. See, maximum power transfer theorem is very simple. Here, say, suppose we are going to connect some variable load across some voltage source, then this constant voltage source, constant practical voltage source, then at what value of load resistance the power consumed by the load resistance is maximum. That is called as the maximum power transfer theorem. Means at what value of the variable resistance the load is going to consume highest amount of power from the source, that we are going to call it as the maximum power transfer theorem. This theorem is applicable only when load is variable. Yes, we have to apply this theorem only whenever the load is a variable. Otherwise, choose the minimum internal impedance of the source which gives maximum current to the fixed load, and it is applicable only when network is linear and applied for both active and passive network. See, this theorem is going to apply only when the load is a variable. Otherwise, if suppose the internal resistance is suppose it's a variable, then we have to, and the load is a fixed, so therefore you are going to get the maximum current only when the internal resistance is 0, then only we can get the highest amount of current. If the current is higher, then we can say simply the load, or we can say simply then the power consumed by the load is also higher. So therefore we can say simply that this theorem is going to applicable only when the load is a variable. Otherwise, choose the minimum internal impedance and then get the maximum current. So maximum current means maximum power consumed by the load resistor. So this is for when the load is a constant, but when the load is a variable, we have to apply this maximum power transfer theorem in order to get advanced value of RL, a maximum amount of power from the source. So now we are going to learn some of the cases which are, suppose this is a ideal DC voltage source. This is a DC voltage source Vs, and this is a, or we can say this is a practical DC voltage source which is Vs and Rs. So we are going to connect a variable load across this practical DC voltage source. Then I want to know at what value of RL this load RL is going to consume huge amount of power from the source, and what is that value I want to figure out, a maximum amount of power consumed by RL at what particular RL. So therefore for maximum power transfer, RL should be always equal to Rs, means the load resistance should be always equal to the internal resistance. So therefore RL is equal to Rs. and the Pmax is equal to Vs square by 4Rs, or we can say 4RL. So therefore this is the value of the things here. So therefore simply we can say Pmax is equal to Vs square by 4Rs, or Rs is equal to RL. So therefore Vs square by 4RL. So therefore whenever RL is equal to Rs, we are going to get the value of current. So with the help of that current, find the value of the power. P is equal to I square RL. So you can keep that equation, current value, and if you solve this one, we are going to get Vs square by 4Rs we are going to get. And if you want to know what is the efficiency at the maximum power transfer condition, which is output power by input power, so definitely output power will be the half of the input power. Suppose input is going to give you 100 watt, means 50 watt is consumed in the internal resistance and 50 watt is consumed in the external resistance. So therefore we can say only half of the part is going to get to the load. So therefore we are going to get only 50%. Means we at maximum power transfer condition, always the power consumed by the load is equal to the power consumed by the internal resistance. Suppose now we are going to consume the AC case. So this is the AC source. Vs is nothing but it is a RMS value. Generally in the examination they are not going to, if they are not specified whether it is a maximum value or AC or RMS, then by default it indicates it is RMS value. And this is a source impedance. Then this is a load, variable load we are going to connect across this practical voltage source, AC voltage source. Then at what value of ZL we are going to get the maximum amount of power absorbed by this source, but by this load we need to figure out. See, Zs is equal to Rs plus Jxs is a complex impedance, means it's a combination of resistance and some inductance. So ZL is equal to RL plus Jxl. So Vs is called as the RMS value of the input voltage. When maximum power transfer, only when RL is variable. See, when RL is variable but XL is a constant, so overall value ZL is going to get vary. So we can say clearly the value of RL at which the maximum power is going to transfer from source to load is equal to RL is equal to under root over RS square plus XS plus XL whole square. It's a very important formula. RL is equal to under root over RS square plus XS plus XL whole square. But if you want to find what is the maximum power transfer, only when XL is variable. If XL is only variable means RL is a constant, but overall value is going to get changed. So at what value of XL variable when RL is a constant, I want to find at what value of XL the maximum power is going to get transferred. When XL is equal to minus XS only, we are going to get the huge amount of maximum power is consumed by this load. Suppose when both are variable, then at what condition the maximum power transfer is going to occur? If both RL and XL are variable, then at what condition we are going to get the maximum power transfer to the load? If both are variable, definitely ZL is also variable. So therefore we can say these two conditions, this we have to substitute, these two conditions should be satisfied. So therefore this equation 1 and equation 2 both should satisfy. So therefore in place of XL substitute minus XS. So you are going to get this term as 0. So then RL is equal to RS and XL is equal to minus XS. So therefore RL is equal to RS and XL is equal to minus XS. So here we can, if you do addition of these two things, we are going to get ZL is equal to RL plus JXL is equal to RS minus JXS. So therefore simply we can say ZL is equal to ZS conjugate or ZS is equal to ZL conjugate. So we can say the load impedance is equal to complex conjugate of the source impedance. Then at that condition, when both RL and XL are variable, at this condition only we are going to get a huge amount of power consumed by this load. So you can see clearly at this condition the inductive part is going to get cancelled in the circuit. So circuit is purely resistive. So at this condition the circuit is purely resistive. And at this condition also you can see clearly the circuit is purely resistive, but not at this condition. At this condition the circuit is not purely resistive. So now we are going to discuss another condition. Suppose the same practical voltage AC source, AC source. So now we are going to consume only, now we are going to keep only RL as a variable. There is nothing like XL. Means XL is equal to 0. I have already told you the formula, which is RL is equal to under root over RS square plus XL whole square. But XL is equal to 0. So therefore substitute here in the equation we are going to get finally RL is equal to under root over RS square plus XL square. At this value of RL, we are going to get the maximum amount of power consumed by this RL from this source. Only the resistor is going to consume the power, but not the inductor or the capacitor. We are going to learn about the reciprocity theorem. In a linear passive bilateral network, the response to excitation ratio is constant even though input and output terminals are interchanged. if the network contains dependent source, then this doesn't satisfy. See, basically, it indicates that suppose there is some linear network. The system should be linear, passive, and also bilateral network. Then only we can say the response to excitation, the ratio of the response to excitation ratio is constant even though input and output terminals are interchanged. If the network contains dependent source, then this doesn't happen. It indicates that the circuit should be purely independent sources. Then definitely if you are going to interchange one source and the response, then the ratio of the response to excitation is always going to get constant. That is the meaning of the reciprocity theorem. Means there has to be an independent source and also the response. See, we are going to interchange their position, still the ratio of the response to excitation will be always going to get constant. That is the meaning of the reciprocity theorem. So you can see clearly here, this is some complex network. It is going to contain only some linear bilateral networks elements. So now this is the voltage source, independent voltage source, and there is nothing like dependent sources in this circuit, and is the response of a circuit I. So now I am going to do the interchange of these two parameters. So now this will become source, the response, and this will become the source. Now the ratio of the response to excitation, which is I by V, is equal to I by V. So we can say clearly, if you are going to interchange the position of the excitation and the response in a linear network without any dependent sources, still the ratio is going to get constant. Then we are going to say that that is called as a reciprocal circuit. So now we are going to learn about the substitution theorem. In a linear network, any branch can be replaced by different branch provided the remaining network voltage and current are undisturbed and the new branch voltage and the current must be same as the previous one. So in a linear network, any branch can be replaced by different branch provided the remaining network voltage and the current are undisturbed and the new branch voltage and current must be same as the previous one. See, basically here the meaning of this is you can replace any branch from a circuit with any other element. Still, even if you are keeping that new branch in that circuit, then the voltage and the current of the remaining circuits shouldn't get changed. Then only we can say this is called as a substitution theorem. Means in place of original, we are going to replace the another branch. Still, the circuit is going to behave like the same. Means the voltage and the current across remaining elements should be same as this one, as the previous one. So you can see clearly here, this is some network. So for this network, you can see clearly here, this is some source E. So this is some resistor R. So because of this network, a current is going to flow through this resistor. Let me assume the current is I and the voltage across the resistor is V. So the voltage across the resistor is V. So now I am going to replace this resistor by some other element. Still, the voltage and the current in all the circuit elements are going to be same as the previous one. So now I am going to replace this resistor by some voltage. This voltage should be equal to the voltage across the resistor. So therefore, I am going to replace with some ideal voltage source. This voltage is equal to voltage across the resistor. So because of this, we can say clearly, still there is no disturbance of voltage and current in the remaining part of the circuit. You can see clearly the current in the resistor is I. So I can replace by current source also. So I can replace this resistor by some current source also, so that the remaining part of the network is not going to get disturbed by, the remaining part of the network is undisturbed with the current and voltages. So we can say clearly, either we can replace by ideal voltage source or either we can replace this resistor by some ideal current source. So this we are going to call it as the substitution. Means we are replacing one parameter, one branch by the new branch, but still there is no change in the current and the voltage in the remaining part of the network. So you can see clearly, I have replaced this by a current source in this downward direction because still the current is I and the voltage is V. So therefore we can say clearly, we have replaced the resistor by either ideal voltage source or ideal current source. The voltage is the voltage across the resistor and the current is the current to the resistor. Still there is no change in the voltage and the current across the remaining part of the network. This we are going to call it as the substitution theorem. So now we are going to learn about the Milliman's theorem. See, Milliman's theorem is, suppose there is some parallel of practical voltage source. So this everything is a practical voltage source of this format, which is R1 V1, R2 V2, R3 V3 up to Rn Vn. So now I want to replace all these with respect to a single practical voltage source. I want to figure out. So all these practical parallel voltage sources I am going to replace with a single practical voltage source. So then what is that equivalent voltage and the equivalent resistance? Now we need to figure out. See, you can apply even the Thevenin theorem also to figure out the Thevenin voltage and the Thevenin resistance. See, if you want the net voltage across VAB, just go for the nodal analysis, then we are going to get the Thevenin voltage is equal to the equivalent voltage. If you want the equivalent resistance, just do the short circuit of all these voltage sources, then we can say the Thevenin resistance is equal to the parallel combination of each of individual resistances. So this is called as equivalent voltage. We can also call it as the Thevenin voltage or the Milliman voltage, and this is the Thevenin resistance or the minimum resistance. So this value Vm is equal to V1 G1 plus V2 G2 up to Vn Gn by G1 plus G2 plus up to Gn. So basically G1 means reciprocal of the resistance. It is also called as a conductance. So G2 is equal to 1 by R2. Similarly, Gn is equal to 1 by Rn. So by this we are going to get the value of the equivalent voltage or the Milliman voltage, which is Vm. See, basically V1, V2, V3 up to Vn are sign sensitive. Means always the upper part is positive and the down part is negative. So that is the convention you should go for this process to get the result. So Thevenin resistance or the minimum resistance is equal to 1 by G1 plus G2 plus up to Gn. So G1 is equal to 1 by R1 plus 1 by R2 plus up to 1 by Rn. So this is the manner you can get a lot of practical voltage sources in parallel. We can replace with a single practical voltage source of Vm and Rm, where Vm formula I have already told you, V1 into G1 plus V2 into G2 up to Vn Gn by G1 plus G2 up to Gn. Similarly, Rm is equal to 1 by G1 plus G2 plus G3 up to Gn. I have already told you that you can even go for the Thevenin circuit, still you are going to get the same result. The only difference is how you are going to solve this question. No matter whatever the method you prefer, still you are going to get the same result. So always this voltage V1, V2 up to Vn are the sign sensitive. Always upper part is positive and the down part is always negative. So this is the point I have written here, which is all the voltage V1, V2, Vn up to are sign sensitive, means always the upper part is positive and the down part is always negative. So this is the thing that you need to remember in your head, then only you can solve that question. So now we are going to learn about the RC circuit. See, this is a resistor and a capacitor. So the voltage across the resistor is VR of t and the voltage across the capacitor is VC of t. See, then I am going to connect this switch at A. So then there is a voltage source. So because of this voltage source, this capacitor is going to get charged. After charging at a steady state, and I am going to remove this switch to, I am going to move this switch to B. So therefore the capacitor is going to get discharged. Then what is the nature of the voltage across the capacitor, voltage across the resistor, and the current through the resistor? We are going to see each and everything in a detailed mode. See, when the switch is at A, because of this voltage source, the capacitor is going to get charged. So we are going to call it as the charging mode. So now we can use this formula, which is Vc of t is equal to Vs into 1 minus e to the power of minus t by Rc. Here Rc is called as a time constant. Means time constant indicates that the voltage across the capacitor is going to, at that time, it is going to reach 63.2% of the final value. That we are going to call it as the time constant. So therefore Vc of t is equal to Vs into 1 minus e to the power of minus t by Rc, because capacitor voltage cannot change instantaneously. So therefore it is going to increase in a slow manner, and steady state it is going to reach the value of the Vs. So if you substitute t is equal to infinity, you are going to get this term as 0. So therefore 1 minus 0 is 1, 1 into Vs is Vs. So therefore at a steady state we can see clearly the voltage across the capacitor is equal to Vs. Initially we assume that the capacitor voltage is 0. So therefore Vc of t is equal to 0 at t is equal to 0. So capacitor voltage cannot change instantaneously. It is always going to change in a very slow manner. And also, if you want to know what is the expression of the current, which is Vs by R into e to the power of minus t by Rc. So you can see clearly here at t is equal to 0, the voltage of the capacitor is 0. So therefore the current will become Vs by R. So this is the initial current or the maximum current, and then it is going to get decay, because the capacitor voltage is going to get increase, means the current is going to get decay. So therefore I of t is equal to Vs by R into e to the power of minus t by Rc. And if you want to know what is the voltage across the resistor, which is supply voltage minus the capacitor voltage, by using the KVL also we can get this expression, which is VR of t is equal to Vs minus Vc of t. So with the help of Vc of t and Vs, we can find the expression of the VR of t. Suppose if you want to know what is the derivative of the voltage at t is equal to 0, means what is the rate of change of voltage of the capacitor at t is equal to 0, means the rate of change of capacitor voltage at t is equal to 0. So if you do the derivative of this expression and if you substitute t is equal to 0, we are going to get Vs by Rc. So Vs by Rc is called as the derivative of the capacitor voltage at t is equal to 0. It indicates that Vs by tau. So therefore simply it indicates that if the capacitor is charged with this initial rate, then within tau is equal to Rc, it is going to charge to the voltage of Vs. So listen carefully. If suppose the capacitor is going to charge with this rate from initial onwards, then within the time tau, it is going to reach the value of the steady state, which is Vs. That is the meaning of this expression. So now we are going to learn about the discharging mode. Means when the capacitor is charged, after some time we are going to move the switch to position B. So because of that, we can say clearly there is no voltage source. So therefore similarly the capacitor itself is going to distribute, or it is going to deliver its energy to the resistor. So because of that, the capacitor voltage is going to get decreased, and then we can say, see here, the voltage is going to get decreased, means the energy in the capacitor is also going to get decay. So therefore the initial value is equal to Vs, so therefore it is going to get decay. The expression of the voltage of the capacitor, which is Vc of t is equal to Vs into e to the power of minus t by Rc. And see, listen carefully, the voltage across the capacitor is the polarity in the same as the previous one, but now this capacitor is going to supply the energy, means the current should be in the opposite manner. Then only we can say the capacitor is going to supply the energy. So therefore I of t now will be reverse of the previous one, which is I of t is equal to minus Vs by R into e to the power of minus t by Rc. So now if you want to know what is the value of VR of t, which is by using the KVL, we can get that VR of t is equal to minus Vc of t. So these are the discharging mode, the equations of the capacitor voltage, the current in the capacitor, and also the voltage across the resistor. So now I am going to draw the capacitor voltage with respect to time in the charging mode and also in the discharging mode. So you can see clearly here in the charging mode. So this is called as the charging mode. In the charging mode, the capacitor voltage is going to get increase in the expression, which is Vs into 1 minus e to the power of minus t by Rc. So by this expression, it is going to get increase in a very slow manner. So at t is equal to tau, we can say clearly it is going to reach 63.2% of the final value. So because of that reason only it is reached 0.63 Vs. So now at 5 tau, at nearly 5 tau, it is going to reach nearly 99.99% of the steady state. So because of that reason we say 5 tau is nothing but the steady state value, means within this time it is going to reach the 99.99% of the final value. So now after reaching the steady state, after some time what I am going to do is I am going to open the switch or move the switch to position B. So because of that, the capacitor voltage is going to get decay. So the expression is Vs into e to the power of minus t by Rc. So with this it is going to get decay. So you can see clearly at tau, means from this time tau it is going to get decay. The decay is nothing but here this much amount of decay is 63%, but if you want from initial it will be 63 minus, means 100 minus 63 is nothing but 36. So 36% of the final value. So we can say clearly this is called as the 0.36 Vs. So within 5 tau it is going to reach the 0 value. So this is the graph of the charging mode and also the discharging mode. I have drawn the current diagram with respect to time in the charging mode and also in the discharging mode. So in the charging mode, the current is going to decay in this manner, which is Vs by R into e to the power of minus t by Rc. So therefore the current is going to get decay. So at t is equal to tau, this is nothing but 63%, but if you want from the origin, it will become 36. So 0.36 times of the final value Vs by R. So within 5 tau it is going to reach the 0. And after some time I move the switch to the position B. So because of that the current will be reversed. Then only we can say the capacitor is going to deliver the energy. So because of that the expression will become minus Vs by R into e to the power of minus t by Rc. So by that it is going to now decay. So therefore at 5 tau it is going to reach the 0 value. So we can say clearly this is called the charging mode or the transient state. So this is steady state. This is again discharging mode or transient state, and this is again the steady state. So these are the diagrams we are going to see of the voltage across the capacitor and the current to the capacitor in the both charging mode and also in the discharging mode, where TS is called as a transient state, whereas SS is called as the steady state. So some of the important points whenever in the circuit we are going to learn, which is during charging mode, initial capacitor acts like a short circuit, and at steady state it acts like open circuit, because during charging mode I have already told you initial capacitor voltage is 0, so therefore it can't change instantaneously, so therefore it will be remain at 0 at t is equal to 0 place. So because of that nature only we are going to assume it is a short circuit. But at steady state the capacitor voltage is going to reach the steady state value is equal to supply voltage. At that condition the current is equal to 0, so it indicates that it is going to act like a open circuit. So therefore we can say whenever you are going to charge the capacitor, initially it is going to act like a short circuit, and finally it is going to act like a open circuit. The voltage across capacitor doesn't changes instantaneously. Yes, the voltage across the capacitor doesn't changes instantaneously. Suppose if it is going to change instantaneously, then it will be a very huge amount of spike in the current is going to get occur, means there will be a lot of amount of spark. So because of that reason only, always the voltage across the capacitor doesn't changes instantaneously, whereas the capacitor is a passive element. See, capacitor is always a passive element, because see, passive elements means it can store the energy, it can deliver the energy, but active element is always going to get deliver the energy. So therefore we can say clearly resistor, inductor and capacitor are said to be passive elements but not an active elements. An active element can do the amplification and also can deliver the energy for infinite time. So because of these reasons we say capacitor is always a passive element. The energy of a capacitor at any instant is E is equal to half C Vc of t whole square. So we can say clearly the energy of a capacitor at any instant is equal to half CV Vc of t whole square, because the capacitor energy formula is E is equal to half CV square. So therefore half C, because we want at any time, so therefore energy is equal to half C Vc of t whole square. So with the help of this voltage across the capacitor at any time, if you know that value, keep it in this value expression and do the simplification, we are going to get the energy of the capacitor at that instant of time. So now we are going to learn about the RL circuit. See, now up to now we learned about the RC. So now we are going to learn about the RL circuit. See, for this RL circuit, we are going to keep the switch at A. So whenever we are going to keep the switch at A, there is a voltage source. So because of this voltage source, this is going to get charged. So therefore this is called a charging mode. But if you move the switch from A to B, there is no voltage source. So therefore this inductor is going to deliver its energy to resistor. So because of that reason we say it is going to decay its energy, or simply we can say it is going to dissipate its energy, or simply we can also say it is a discharging mode. So in the charging mode, the current in the inductor cannot change instantaneously. So because of that reason only, we can say the current is going to increase in a very slow manner. So initially the conductor is going to act like an open circuit, whereas finally it is going to act like a short circuit. So because of that reason, we can simply say the expression of the current is equal to Vs by R into 1 minus e to the power of minus t by tau, where tau is equal to L by R. So you are going to get this expression. So now here this is the charging mode case. So voltage across the resistor is VR of t, and the voltage across the inductor is VL of t, and I of t is the current in the circuit. So now VL of t is equal to, as the current is going to get increase, the current is going to get increase means the resistance voltage is also going to get increase. So definitely VL of t will be decreased, then only Vs is constant. So therefore VL will decay. So VL of t is equal to Vs into e to the power of minus t by tau. The tau is equal to L by R. So otherwise you can also find with the help of the VL is equal to L into di of t by dt. So if you know di of t dt into L, you are going to get the value of VL of t. So therefore now if you want to know what is the value of VL of t, which is Vs minus VL of t. So with the help of these things, you can also get the value of the VL of t. So I of t is equal to Vs by R into 1 minus e to the power of minus t by tau. The tau is equal to L by R, and VL of t is equal to Vs into e to the power of minus t by tau. The tau is equal to L by R, and VL of t is equal to Vs minus VL of t. So now we are going to learn about the discharging mode. See, discharging mode means now we move the switch position to B. So because of that, there is no voltage source in order for inductor to get charged. So because of that reason, the inductor is going to deliver its energy into resistor. So now the current in a inductor cannot change instantaneously, direction also it cannot change. So because of that reason only, this voltage across the inductor is going to get changed, then only we can say it is going to deliver the energy. So therefore now I of t is equal to ds by r into e to the power of minus t by tau, where tau is equal to L by r. And VL of t, if you know the value of I of t, and if you do the derivative with respect to time, and if you multiply by L, we are going to get VL of t is equal to minus Vs into e to the power of minus t by tau. Tau is equal to L by r. I have already told it is negative, then only it can deliver the energy. And also, by if you apply the KVL in this loop, we are going to get VR of t is equal to minus VL of t. So if you know this value, you substitute here, you are going to get the value of the VR of t. So now I am going to draw the diagrams of current in the inductor and also voltage across the inductor with respect to time for charging mode and also in the discharge mode. See, current in the inductor cannot change instantaneously, so it is going to increase in a very slow manner in a charging mode. So initial current is 0 because it is an open circuit. So we have assumed the current in the inductor is 0 at initial. So therefore, this 0 at t is equal to 0. At a steady state, it is going to become charged. The current is going to become maximum. So therefore, here it will act like a short circuit. So therefore, initially open circuit and finally short circuit. So final value is Vs by R and initial value is 0. So within 5 tau, it is going to reach the maximum value. So at t is equal to tau, it is going to become 63.2% of the maximum value. So this is the charging mode. Similarly, in the charging mode, the voltage across the inductor is going to get decay. So therefore now VL of t is equal to Vs into e to the power of minus t by tau. So because of that, it is going to get decay. So within 5 tau, it is going to reach the value of 0. So we can say if this is 63% means this value will become now 36%. So 36% of the final value. So at steady state, it is going to reach the maximum value. If the current is maximum, then diffusion of current is 0. So because of that, the voltage will be 0 across the inductor. So now we have moved the switch from A to B. So therefore, this is in the mode of the discharging mode. So current is going to get decay. But the current is going to get decay with the expression which is Vs by R into e to the power of minus t by tau. The tau is equal to L by R. So therefore, within tau, if this is 63% means this value will be 36%. So therefore, we can say 0.36 times of final value. And within 5 tau, it is going to reach the value of 0. But here I have already told you, VL of t will be minus Vs into e to the power of minus t by tau. Because of that nature, it is going to go in this direction. Then only we can say it is going to deliver the energy. So therefore, now we can see clearly it is going to decay in this manner. So therefore, within the time period of 5 tau, it is going to reach the value of the 0. So this is transient state, this is a steady state, again this is transient state, again this is steady state. So simply we can say this is a charging mode and this is a discharging mode. So TS is also called the transient state and SS means steady state. So now we'll discuss some more important point in the RL circuit. During charging mode, we replace inductor by open circuit at initial stage and replace inductor by short circuit at steady state, and it acts like a passive element. I have already told you in the charging mode, inductor initially we assume current is equal to 0. Then because of that reason, at initial stage it is going to act like a open circuit, and at steady state the current will become maximum. So derivative of maximum value will become constant value will become 0. It indicates the voltage across the inductor is 0 at steady state. So therefore we can say clearly it is going to act like a short circuit at steady state. And also inductor is always a passive element because there is no internal amplification, or it can supply the energy for a lot of time. So because of that reason, we can say inductor is always a passive element. Inductor won't allow sudden change in current. Yes, the capacitor won't allow sudden change in voltage, and similarly inductor won't allow sudden change in current. During discharging mode at any steady state, the current is 0. So during discharging mode at steady state, the current is 0. Yes, I already told you during the steady state, because it is going to get decay. So now the current is going to get decay. So because of that, at steady state it will become 0. And inductor is always act like an active element in this period. Only in the discharging mode it is going to act like an active element, means it is going to deliver the energy. But overall we can say it is a passive element. So therefore, energy in an inductor at any time is equal to half Li square. So therefore, if you want at any time, means if you know the current at any time, just substitute in this formula, you are going to get the energy in the inductor at any time. So now we are going to learn about the other concept, which is the equivalent circuit. See, we are going to draw the equivalent circuit of inductor and capacitor. See clearly, this is an inductor. So inductor, the current in the inductor is IL of t, and the voltage across the inductor is VL of t. So now for minus infinity to plus infinity, so within this time we are going to write the expression of this inductor current. So therefore now what is going to happen is, then suppose if I want to know what is the value of the inductor current at a particular time, so therefore IL of t is equal to 1 by L into integration of minus infinity to t VL of t into dt, because VL of t is equal to L into di by dt. So therefore IL of t is equal to 1 by L into integration of minus infinity to t VL of t dt. So we can split this integration into two parts, from minus infinity to 0 plus 0 to t. So we can split the inductor current into two parts. So therefore now I am going to assume the current from minus infinity to 0 is nothing but some value of I naught. So therefore this is the same take as the previous one. So we can say clearly IL of t is equal to I naught plus 1 by L integration of 0 to t VL of t into dt. So I am going to assume this is nothing but I1 of t. So therefore IL of t is equal to I naught plus I1 of t. So I can draw the circuit in this fashion, which is here VL of t and this is IL of t, same previous one, same inductor is L, but here now it is I1 of t and this is a constant current of I naught. So this is a circuit for t greater than or equal to 0, but this is a circuit from minus infinity to particular time t, but this is for t greater than or equal to 0. So because of that reason only this is equivalent to this one. So if by using the KCL we can tell IL of t is equal to I1 of t plus I naught, where I1 is equal to 1 by L into integration of 0 to t VL of t dt, whereas I naught is equal to 1 by L integration of minus infinity to 0 VL of t into dt. So we can write this circuit into this circuit also. So now what I am going to do is, I am going to convert this circuit into Laplace domain. So this is going to become VL of s, IL of s, this will become SL, and this will become I naught by S. So same thing I have drawn here, VL of s, IL of s, SL, I naught by S. So I am going to convert this practical current source into a practical voltage source. So the practical voltage source is nothing but product of these two values. If we do the product of these two values, we are going to get L into I naught, and the polarity positive is downward and the negative is upward. So positive is downward, negative is upward, which is L into I naught. And if you want to know what is the internal resistance, which is same SL, so ASL. So we can go for the conversion. You can apply this one or you can apply this one. Any of the thing you can apply to solve the things. So now we are going to know the concept of the capacitor. So for a capacitor, if this is a capacitor C, then you can see clearly I want to draw equivalent circuit of a capacitor. So this is, let me assume the capacitor voltage is VC of t and the current to the capacitor is IC of t. So this is a circuit from minus infinity to particular time t. Then what I am going to do is, I am going to know the expression of the capacitor voltage, which is I is equal to C dV by dt. So therefore VC of t is equal to 1 by C into integration of minus infinity to t IC of t dt. So I want the value of capacitor voltage at a certain point t. See, I can substitute, I can replace this integration into, or I can divide this integration into two parts, from minus infinity to 0 plus 0 to t. Therefore VC of t is equal to 1 by C integration of minus infinity to 0 IC of t into dt plus 1 by C integration of 0 to t IC of t dt. So I am going to assume this has some voltage V0, initial voltage V0, and this is the original voltage. So VC of t is equal to initial voltage plus 1 by C integration of 0 to t IC of t dt. So now I can replace this circuit into this circuit, which is here VC of t is equal to, this is V0 plus, here this is nothing but here this voltage will become 1 by C into integration of 0 to t VC of t dt, because this is for, see, this is nothing but here this voltage will become now here this voltage will become 1 by C integration of 0 to t IC of t dt. So therefore it is a combination of these two things. So VC of t is equal to V0 plus 1 by C integration of 0 to t IC of t dt. So this is for t greater than or equal to circuit, but this is for all the range, or simply we can say from minus infinity to t, or this is for t greater than or equal to 0. So now I am going to apply the Laplace transform, then I am going to get VC of s, IC of s, V0 by s and 1 by SC. So then I am going to convert this into practical current source. So VC of s, IC of s, V0 by s, 1 by SC. So now this is a practical voltage source. I am going to convert into practical current source. So current is equal to voltage by resistor. So if you do the division of these two things, V0 by s by 1 by SC, we are going to get here V0 by C. So simply we can say here V0 into C we are going to get. So therefore V0 by S by 1 by SC is nothing but here V naught into C current source. The positive is upward and the negative is downward. So therefore, arrow is upward, the tail is downward, and this you should do in a parallel manner. So therefore, this is the value or equivalent circuit you are going to get. So therefore, you can go for either this one or either this one. So you are going to get the same result. So if you apply the KVL, we are going to get Vc of t is equal to V naught plus 1 by C integration of 0 to t Ic of t dt. So now we are going to learn about the steady state response. Steady state response means we are going to neglect the transient response. Only we are going to see the steady state. We are going to neglect the transient response, but only we are going to learn about the steady state. So therefore, let me take a system which is going to have input is Vi of s and the output is V naught of s, and h of s is a transfer function of the system. So therefore, h of s is equal to output by input. So therefore, h of s is equal to the transfer function of system is equal to Laplace transform of output by the Laplace transform of input. So therefore, h of s is equal to V naught of s by Vi of s, where s is equal to j omega. So let me assume that input time domain expression is Vi of t is equal to ai into sine of omega naught t plus phi I. Then what is the nature of the output voltage? Which is, see, the system is going to do only two things. It can either amplify the signal or decay the signal, or it can give a some amount of phase shift to the input signal. Only these two things it can do, but can't change the frequency of the signal. So therefore we can say this system can only either amplify the signal or decay the signal, and it can also shift the signal, but it can't change the frequency of the signal at the output. So therefore ai sine omega naught t plus phi I can become, now here the amplified output will be here h of s. Now you can, it's a complex number, you can go for the magnitude and also the polar part. So therefore the magnitude of hs into ai sine of omega naught t plus phi I plus angle part of h of s, that is the net output equation. So you can see clearly here ai into mod of h of s at omega is equal to omega naught at a particular frequency, and sine of omega naught t plus phi I plus angle of h of s at omega is equal to omega naught. So this is called as the net output equation, means either amplitude can be either gained or decay, but only it can phase shift by this much amount of factor. So therefore V naught of t is equal to ai into mod of h of s omega is equal to omega naught sine of omega naught t plus phi I plus angle of h of s at omega is equal to omega naught. So this is the net output equation of a linear network. So this is called as a steady state response of the output equation, means it can only gain by this factor, and this is the amount of phase shift. So now we are going to learn about the AC transient free response. So for AC transient free response means, suppose AC transient free response means we are going to, by some condition, we can remove the transient response. So what is that condition now we are going to see? See, suppose RL circuit, this is basically an RL circuit, and we are going to switch this switch. There is a switch here. We are going to close this switch at T0. At what instant, if you do the switching, then we can say that there will be no transient. See, listen carefully. At what amount of time, if you are going to close this switch, then we can say that there will be no transient response in the inductor current. So therefore, inductor current at the T0, it is going to have only steady state, but there is no transient response. So what is the transient time T0? That is T0 we need to figure out. So basically here, this I of t is going to contain both transient and also steady state. Suppose if input voltage is equal to, there are two cases for this one based on the input voltage. If Vi of t is equal to Vm sine omega t plus phi, it is a sine voltage. Then at t is equal to T0 switch is closed, then I of t will have no transient response when the condition is here omega t plus phi at T0 is equal to tan inverse of omega L by R. At this condition only, we can say that there will be no transient response in the current I of t. So therefore, omega t plus phi at T0 is equal to tan inverse of omega L by R. At this condition only, we can blindly say that there will be no amount of transient response is not going to present in the I of t current. So omega t plus phi at T0 is equal to tan inverse of omega L by R. Yes, to if the input Vi of t is equal to Vm cos of omega t plus phi, yes, the only thing is we have changed the input from sine to cos, then what is going to happen? Which is at t is equal to t naught, switch is closed. Switch is closed. Then what we can say that at the time t naught, if you are going to close the switch at that t naught, then definitely the current I of t will not have any transient response. It will only have the steady state. Then omega t plus phi at t naught is equal to pi by 2 plus tan inverse of omega L by R. See, only extra is we have to go for the pi by 2 addition here. There is the only thing that you need to do addition. So therefore we can say omega t plus phi at t naught is equal to pi by 2 plus tan inverse of omega L by R. So for sine there will be no pi by 2, but for only cos there will be a pi by 2 term, extra term. That is the only difference. For sine there will be no particular pi by 2, only for sine, only for cos there will be an extra term of pi by 2. So omega t plus phi at t naught is equal to tan inverse of omega L by R for sine to, when the input is in the function of sine, whereas omega t plus phi is equal to pi by 2 plus tan inverse of omega L by R when the input is in the term of the cos. Suppose for RC circuit, now we are going to see here. So until now we learned about the RL circuit transient free response. So now we are going to learn about the transient free response for RC circuit. See, same thing here, the voltage across the inductor is definitely going to have the transient response and also steady state, but I am going to close the switch at t naught, so therefore definitely we can say that at that condition the capacitor voltage will not have any transient, it will only have the steady state. So what is that t naught we need to figure out? So therefore definitely we can say that here when I am going to consider two cases for the input, same as the previous one. So case 1, which is Vi of t is equal to Vm sine of omega t plus phi. At t is equal to t naught, the switch is closed, so therefore definitely we can say at the t naught there will be no transient response in the Vc of t. The expression is omega t plus phi at t naught is equal to tan inverse of omega Rc. Tan inverse of omega Rc. So therefore we can say clearly that here at this condition only we can say there will be no transient response in the capacitor voltage. So therefore whenever the input Vi of t is equal to Vm sine omega t plus phi, then at omega t plus phi at t naught is equal to tan inverse of omega Rc, then we can say there will be no transient response. But if you go for the cos, just you have to add here pi by 2 extra term. So case 2, which is Vi of t is equal to Vm cos of omega t plus phi, at t is equal to t naught, I am going to close the switch. So we can say clearly then Vc of t will have no transient, or we can say there will be no transient response, means it is free from transient response. It is going to have only steady state term, that t naught is equal to omega t plus phi, t naught is equal to pi by 2 plus tan inverse of omega Rc. So this is the only thing. For sine there will be no pi by 2 term, only for cos we have to go for the extra factor of pi by 2. For tan inverse, means for RL we have to go for tan inverse of omega L by R. For RC just we have to go for the tan inverse of omega Rc. This is the only difference. So now we are going to learn about the resistor behavior to AC source. See, what is the nature of the resistor for the voltage source we are going to see. Suppose what is the resistor behavior for the AC source we are going to see. So this is the voltage source, AC source voltage is V of t, and the current drawn by the resistor R is I of t. So now we are going to analyze this circuit. Analysis, which is here voltage, supply voltage V of t is equal to Vm sin omega t. So current I of t is equal to voltage by resistor. So V of t by R. So if you substitute V of t here, we are going to get I of t is equal to Vm sin omega t by R, or simply we can say Vm by R into sin omega t. So therefore I am going to assume that Vm by R is nothing but peak value of Im. So therefore I of t is equal to Im sin omega t. See, now I want to know what is the power expression, or the power, the instantaneous power across the resistor R, which is voltage into current. It is the voltage across the resistor and the current in the inductor, the resistor. So therefore P of t is equal to V of t into I of t. So if you do the multiplication of these two things, and if you simplify, finally we are going to get P of t is equal to Vm Im by 2 into 1 minus cos 2 omega t. So you can see clearly the power is twice the frequency of the, it is going to have twice the frequency of the both supply voltage and the supply current. So therefore we can see clearly the supply voltage and the supply current will have same frequency, but the supply means the power frequency will be double that of the voltage and the current. So suppose if you want to know what is the phase difference, because there is no phase difference between the supply voltage and supply current. So V, capital V is called as the RMS value, and the capital I is called as the RMS value of the current. So capital V is the RMS value of the supply voltage, and I is called, the capital I is called as the RMS value of the supply current. So therefore we can say clearly both are in phase, but the value of I is somewhat lesser because it is a ratio of R. So because of that, it will be somewhat lesser than V. So because of that, there is no phase difference, means they are going to lie in the same phase, or they are going to coincide with each other, because there is no phase difference. So now I want to know what is the average value of the power. See, there is a two parts. There are two components which are Vm Im by 2 minus Vm Im by 2 into cos 2 omega t. So because of that, there is a cos nature. The second term is going to become 0, because we can say integration over one time period is equal to 0. So because of that, only the constant part we are going to left over, which is PRH is equal to Vm Im by 2. So this is called as the Vm by root 2 into Im by root 2, which is capital V into capital I, where capital V is the RMS value of supply voltage and the capital I is the RMS value of the supply current. So therefore capital V is equal to RMS value of the supply voltage, which is Vm by root 2, and the capital I is equal to the RMS value of the supply current, which is Im by root 2. So now we are going to learn about the inductor behavior to AC source. So what is the nature of the behavior of the inductor to the AC source? Now we are going to learn here. See, this is a voltage across the inductor. So V of t we are going to apply across the inductor, and the current to the inductor is I of t. So now we are going to do the analysis of this circuit. So supply voltage is equal to V of t is equal to Vm sin omega t. So the voltage across the inductor and the current to the inductor is V of t is equal to L into d by dt of di of t by dt. V of t is the voltage across the inductor, and the I of t is the current in the inductor. So if you do the differentiation of these things, then definitely we are going to get I of t is equal to Vm by omega L into sin of omega t minus 90, because in an inductor the current is going to get lagged by 90 degree. So therefore we can say clearly that here we are going to get I of t is equal to Vm by omega L into sin of omega t minus 90 degree. So here omega L is called as the XL. We are going to write a representation of XL. So Vm by omega L or XL we are going to assume it as Im. So therefore I of t is equal to Im into sin omega t minus 90. So if you are going to draw in terms of phasor diagram, so this is V is the capital voltage, or we can say RMS value of the supply voltage, and the I is the RMS value of the supply current. So current is always going to lag. Minus means 90. So it is going to lag the supply voltage by 90 degree. Positive means anti-clockwise, negative means clockwise. So because of it will become I. So the phase difference between the supply voltage and supply current is 90 degree. So if we want to know what is the instantaneous power expression, which is across the inductor, P of t is equal to V of t into I of t. So if you do the multiplication of these two parameters, then finally we are going to get P of t is equal to Vm Im by 2 into sin 2 omega t. So this is the expression we are going to get. So if you want to know what is the average power consumed by the inductor is equal to, then if you do the integration with respect to one time period, so integration of sin 2 omega t in a one time period will be equal to 0. It indicates that it will be 0. It indicates that for half of the time period, the inductor is going to consume the energy, and for remaining half of the period, the inductor is going to supply the energy to the source. So because of that, in a given net time period, no energy is going to present, or it is going to given. So therefore simply we can say the power consumed by the inductor is equal to 0, or the average power consumed by the inductor is equal to 0. Capital V is equal to RMS value of supply voltage, which is Vm by root 2, and capital I is equal to RMS value of the supply current, which is Im by root 2. So now we are going to learn about the capacitor behavior to the AC source. Means what is the behavior of the capacitor when we are going to connect to the voltage source. So the voltage source expression is V of t, and the current to the capacitor is I of t. So what we are going to do is simply easier. See, we are going to do the analysis of this circuit. So analysis, supply voltage is equal to Vm sin omega t. So therefore here current in a capacitor, the expression of the current and the voltage is I of t is equal to C dV by dt. So I of t is equal to, if you do the derivative of this one and if you simplify this one, we are going to get finally Vm by 1 by omega c into sin of omega t plus 90. So you can see clearly there is a positive means anti-clockwise, means the current is going to lead the supply voltage by 90 degree. So therefore I of t is equal to Vm by xc into sin of omega t plus 90. Xc I am going to assume it is 1 by omega c. So Vm by xc I am going to assume it is Im. So therefore Im into sin of omega t plus 90. So current is going to lead the supply voltage by 90 degree. So therefore you can see clearly there is a phase difference of 90 between the supply voltage and the supply current. So now I want to know what is the expression of the power across the capacitor, which is V of t into I of t, where V of t is the voltage across the capacitor and I of t is the current in a capacitor. So if you do the multiplication of these two quantities, then finally you are going to get Vm Im by 2 into sin 2 omega t. So if you want to know what is the average power consumed by the capacitor, which is means you have to do the integration over one time period. So in over one time period, the integration of sine signal is always going to give you 0. So because of that reason, we can say that the average power consumed by the capacitor is 0, means for half of the time period it is going to absorb the energy, and for remaining half of the time it is going to deliver the energy. So because of that, in the net one time period, the energy power consumed by the capacitor is 0. So now the capital V is equal to RMS value of the supply voltage, which is Vm by root 2, and I is called as the current in a current to the circuit, which is the RMS value is equal to the current of the RMS value of the current is equal to Im by root 2. Now we are going to discuss about the RL circuit behavior to AC source. So basically, what is the nature of the RL circuit behavior to AC source? Suppose the source voltage is V of t and we are going to connect to the RL load. So therefore, what is the nature of the current and also the voltage, we are going to discuss each and everything. So here XL is equal to omega into L. This is called as the inductive reactance, which is omega times of L. So now I am going to do the analysis part of this circuit. So now here the base mode, you can see clearly always the current is, I am going to take the current as a phasor. So the voltage across the resistor and the current are in same phase, whereas in the inductor the current is going to lag the voltage across the inductor by 90 degree. So I have drawn in this fashion. So therefore, but overall, if you do the vector sum of the voltage across the resistor plus voltage across the inductor, it is equal to the supply voltage V. So therefore, we can say V is called as the supply voltage and VR is the voltage across the resistor and VL is the voltage across the inductor. So therefore, this is called as the theta, or we can even call as the power factor angle. So now here what I am going to do is now, but VR is equal to I into R and VL is equal to I into XL, whereas V is equal to I into mod Z. So if I am going to cancel I on the three sides, I am going to get R, XL and mod Z. The angle of theta is very similar because these are the similar triangles. So now I am going to multiply I for each and every term. So VR into I is nothing but P, active power consumed by the resistor, and BL into I is called as the reactive power consumed by the inductor, and VI into I is the complex power sent by the source. So therefore we can say SPQL. So all these three triangles are similar triangles. So therefore the angle theta is same for each and every triangle. So now by using the Pythagoras theorem, we can say that mod Z is equal to under root over R square plus XL square. Similarly, V is equal to under root over VR square plus VL square. And S is equal to under root over P square plus QL square. So therefore, if you are going to write in the rectangular format, which is Z is equal to R plus JXL. So if you are going to convert into polar format, which is mod Z at an angle of theta. So mod Z is equal to under root over R square plus XL square, whereas theta is equal to tan inverse of XL by R. Suppose if you want to know what is the power factor angle, which is cos theta is equal to VR by mod Z or P by S, because the current is going to lag the supply voltage. So we are going to say it as a lagging power factor. So whenever the current is going to lag the voltage, we say it as a lagging power factor, and if the current is going to lead the supply voltage, then we say it as a leading power factor. Always we are going to take the voltage as the reference vector. Then the amount of power, or we can say the instantaneous power, is equal to supply voltage into supply current. So if you are going to multiply the supply, if you are going to multiply both the supply voltage and the supply current, then you are going to get the expression, which is the average power is equal to Vm Im by 2 into cos theta. So we can write this P average, or simply we can write P. So therefore we can say clearly the average amount of power consumed by the RL load is equal to Vm Im by 2 into cos theta, or simply we can say Vrms into Irms into cos theta. See, only the resistor is going to consume the active power, means this average power is going to consume only by the resistor but not the inductor. So therefore we can also write which is IRMS square R. So P average is equal to IRMS square R, which is I square R. So therefore here is also equal to same this value, which is VI cos theta, because VRMS is Vm by root 2 into Im by root 2 into cos theta. So therefore you can go for any of this expression, still you are going to get the same result. And also here QL is equal to I square XL. So therefore this we are going to call it as the reactive power consumed by the inductor, which is I square XL, which is you can also write which is VI into sin theta. So this is called as the VI into sin theta. So if you want to know what is the value of S, S is the under root over P square plus QL square. So if you do this one, we are going to get I square mod Z. So simply we can say I square into mod Z, or also we can write which is V into I. So therefore VRMS into IRMS. You can write any of the things, because if you take the square root of these things, we are going to get VI. So therefore P is equal to I square R is equal to VI cos theta, Q is equal to I square XL is equal to VI sin theta, whereas S is equal to I square mod Z is equal to VI. So you can go for any of the expression, you are going to get the same result. So capital V is called as the RMS voltage of the supply voltage, and capital I is called as the RMS current of the RMS value of the supply current. So now we are going to learn about the RC series circuit behavior to AC source. So RC series circuit behavior to AC source means there is a supply voltage of V of t and there is a resistor and capacitor. So we are going to pass it through we are going to connect this voltage source. So there will be a current I of t is going to flow through this circuit. So the capacitor reactance is equal to Xc is equal to 1 by omega C. So now we are going to do the analysis of this circuit, which is Z is equal to R minus JXc, where Xc is equal to 1 by omega C. So this is called as the rectangular format. If you are going to convert into polar format, which is mod Z at angle of minus theta. So mod Z is equal to under root over R square plus X square, whereas theta is equal to tan inverse of Xc by R. Here the base plate is R. So if you are going to take the current as a reference, because current is same for resistor and capacitor, so I am going to take current as a phasor. So in a resistor, the voltage across the resistor and the current in a resistor are in phase. So because of that reason I have written here VR. And here in capacitor, the current is going to lead the voltage across the capacitor by 90 degrees. So therefore current is going to lead the voltage across the capacitor by 90 degrees. So therefore VC will be downward. So now if you do the vector addition of VR and VC, we are going to get the supply voltage. And the theta is called as the power factor angle, which is the angle between the supply voltage and the supply current. So here VR is equal to I into R and VC is equal to I into XC, whereas V is equal to I into mod Z. So if you are going to cancel all these I parts, we are going to get R, XC and mod Z. So because these two are the similar triangles, so theta will be same as the previous triangle. And suppose if you are going to multiply by I for each and every side, we are going to get PR into I is called as the P, whereas VC into I is called as the QC, whereas V into I is called as the S. So therefore we can say that if you are going to apply the Pythagoras theorem for each and every triangle, because all these triangles are the similar triangles, so therefore theta is same for each and every triangle. So by using the Pythagoras theorem, we say that mod Z is equal to under root over R square plus X square, whereas V is equal to under root over BR square plus VC square, whereas S is equal to under root over P square plus QC square. And if you want to know what is the power factor, which is cos theta is equal to VR by V is equal to R by mod Z is equal to P by S, which is adjacent by the hypotenuse. It will be always in a leading manner, because the supply current is going to lead the supply voltage by angle theta. So we are going to call it as the leading power factor. And if you want to know what is the instantaneous power expression, take the product of the supply voltage and the supply current. And if you want to know what is the average power which is consumed by the load, then if you do the average power, finally we are going to get Vm Im by 2 into cos theta, or simply we can say Vrms into Irms into cos theta. So which is capital V into capital I into cos theta. So this much amount of average power is only consumed by the resistor but not the capacitor. So therefore we can say P is equal to IRMS square R is equal to VI cos theta, and QC is equal to I square XC is equal to VI sin theta. And if you want to know what is the value of S, it is under root over P square plus QC square. So if you do this one, we are going to get I square into mod Z, or if you go for this process, we are going to get V into I, where capital V is called as the RMS value of the supply voltage and capital I is called as the RMS value of the supply current. So you can go for any of this formula, still you are going to get the same result. So now we are going to learn about the another circuit, which is RLC series circuit behavior to AC source. So we are going to study what is the nature of this RLC series circuit when we are going to apply a AC voltage source. So because of this AC voltage source, the current is going to flow through these three elements, which is I of t. And here XL is called as the inductive reactance, which is omega into L, and XC is called as the capacitive reactance, which is 1 by omega C. So if you want to do the analysis of the circuit, which is these three elements are in series fashion, so therefore we can say Z is equal to R plus JXL or minus JXC. So if you take J as a common, we are going to get J of XL minus XC, where XL is equal to omega L and XC is equal to 1 by omega C. So if you want to know the magnitude part, which is, if you want to convert this into a polar format, so we are going to get mod Z angle theta, where mod Z is equal to under root over R square plus XL minus XC whole square, whereas theta is equal to tan inverse of XL minus XC by R. See, when XL is equal to XC, we can say this imaginary part will become 0. So therefore, Z is equal to R. So simply we say it is a resistive circuit. So therefore, there is no phase angle between the supply voltage and supply current. So we simply say it is a unity power factor network. When XL is greater than XC, we say it is a positive value. So it looks like a inductive circuit. So therefore, current is going to lag the supply voltage. So we say it is a lagging network. Whenever X is greater than XL, then this overall part will become negative. So therefore, it is going to act like a capacitor network. In a capacitor network, always current is going to lead the supply voltage. So we say it as a leading network. So now we are going to analyze the circuit when XL is greater than XC. Means the circuit is going to act purely like a inductive circuit. As the current is same for each and every element, I am going to take current as a reference. So in a resistor, the current and the voltage are in the same phase. So therefore, but in a inductor, the current is going to lag the supply. The current is going to lag the inductor voltage by 90 degrees. So therefore, this is VL. This vector is VL. But in a capacitor, the current is going to lead the voltage across the capacitor by 90 degrees. So therefore, this VC is going to get lagged. So now I have already told you XL is greater than XC. So therefore, VL is equal to XL into I, whereas VC is equal to XC into I. So therefore, definitely VL is greater than the VC. So therefore, this vector is higher than this vector. So if you take the subtraction of these two vectors, if you do the subtraction of these two vectors, then definitely you are going to get this component, which is VL minus VC. VL minus VC. So now, if you take the vector addition of these two vectors, we are going to get the value of the overall voltage, which is V. So therefore, now we can say simply that this is called as the overall supply voltage. This we are going to call it as the overall supply voltage. So therefore, now here V is equal to under root over VR square plus VL minus VC whole square. Suppose here VR is equal to I into R, VL minus VC is equal to I of XL minus XC, and similarly V is equal to I into mod Z. So if you take I component cancel on each and every side, we are going to get R, XL minus XC, and this is mod Z. And these two are the similar triangles, so theta is same. The theta is the angle between the supply current and the supply voltage. So it is called as a power factor angle. Suppose if you are going to multiply by I for each and every side, we are going to get VR into I is called as a P, whereas VL into I minus VC into I, which is called as a QL minus QC. QL minus QC. And here V into I is called as a complex power S. So therefore, now by using the Pythagoras theorem, we know that V is equal to under root over VR square plus VL minus VC whole square. Similarly, mod Z is equal to under root over R square plus XL minus XC whole square. Similarly, S is equal to under root over P square plus QL minus QC whole square. So here QL is called as the reactive power consumed by the inductor, whereas QC is called as the reactive power consumed by the capacitor. So QL minus QC. So therefore, power factor is equal to cos theta, which is equal to adjacent side by the opposite, adjacent by the hypotenuse, which is R by mod Z, or VR by V, or P by S. So you can go for any of the expressions, still you are going to get the same result. So you can see clearly the current is going to lag the supply voltage. So we say this as the lagging network. So now let me assume the capital V is the RMS value of the supply voltage and the capital I is the RMS value of the supply current. So therefore, we can say simply The average power is going to only consumed by the resistor but not the inductor and capacitor. So therefore P is equal to IRMS square R, or also we can write, which is VI cos theta. And if you want to know what is the QL, this QL is equal to I square XL, whereas QC is equal to I square XC. So if you want to know what is the difference QL minus QC, which is nothing but VI sin theta. So therefore, whereas S is equal to I square mod Z, I square into mod Z. By using the same formula, we are going to get this one, which is under root over K square plus QL minus QC whole square. So if you apply this one, we are going to get S is equal to I square mod Z. Or also we can write, which is V into I. So therefore, or simply we can write V into I also we can write. So therefore, P is equal to I square R is equal to VI cos theta, and QL minus QC is equal to I square into XL minus XC is equal to VI sin theta, whereas S is equal to I square mod Z is equal to V into I. So you can go for any of the formula, still you are going to get the same result. So now we will discuss about the RL parallel circuit. So there is a resistor and an inductor. If both are in parallel, then we are going to study what is the phenomena are going to apply if you are going to apply the supply voltage of V of t. So we are going to apply the supply voltage V of t across R and L. So R is going to drive some amount of current which is called as the IR of t, and the current is the inductor is going to consume is going to drive some amount of current which is called as the IL of t. So if you do the summation of these two things, we are going to get the supply current which is I of t. So V of t is the supply voltage and I of t is the supply current. So XL is equal to omega L. So this is a RL parallel circuit. So because this is a parallel circuit, so by using the net impedance, which is 1 by Z is equal to 1 by R plus 1 by JXL, because this is a impedance network, so therefore this is a J omega L, so therefore JXL. So 1 by Z is equal to 1 by R plus 1 by JXL. So now what I am going to do is here, I am going to do the cross multiplication J by J. So J by J square is nothing but minus J. So therefore we are going to get 1 by Z is equal to 1 by R minus J by XL. So 1 by Z is called as the admittance, and 1 by R is called as the conductance, and 1 by XL is called as the susceptance. So therefore Z is called as the impedance, resistance, this is called as the reactance. So the reverse will become admittance, conductance and susceptance. So therefore Y is equal to G minus J DL. So because the voltage is same across the two elements, because they are currently in a parallel, so we can say simply that here we are taking the voltage as the reference in a parallel circuit. But you can see clearly in a resistor the current IR and the voltage are same because they are in phase. So this is IR. But in an inductor the current is going to lag the supply voltage. So therefore the current is going to lag the supply voltage. So if you want the net current, just do the vector addition. This is called as the overall supply current. So now I is equal to, by using the Pythagoras theorem, I is equal to under root over IR square plus IL square, where theta is the angle between the supply voltage and the supply current. But I is equal to, see, IR is equal to V by R, or simply we can say V into G. And similarly IL is equal to V by J or V by XL. So therefore we can say V by XL means V into BL. So therefore V into BL, this part is, and I is equal to V by mod Z, or simply we can say V into mod Y. So therefore if you cancel all the V terms, we are going to get G, BL and mod Y, and these two are the similar triangles, so theta will be same as this triangle. But if you are going to multiply by some more factor, which is V, if you multiply the V for each and every side, we are going to get V into IR, it is called as the P, whereas V into XL is called as the QL, whereas V into I is called as the S. So therefore these three are the similar triangles, so theta is same as the previous one. So by using the Pythagoras theorem, I is equal to under root over IR square plus IL square, and mod Y is equal to under root over G square plus BL square, and S is equal to under root over P square plus QL square. Whereas power factor is called as the cos theta, which is ratio of the adjacent by the hypotenuse, which is IR by I, G by mod Y and P by S. So always you can see clearly the current is going to lag the supply voltage. So we can say it is a lagging power factor. See, no matter whether you connect the resistor and inductor in series or in parallel, always it is a lagging power factor. Means we can say simply the current is going to lag the supply voltage. So if you want the value of P, so P is called as I have already told you here, V into IR. So V into IR, or IR we can write V by R. So therefore V square into G. So V square into G, whereas QL is equal to, so QL is equal to V into IL, or simply V into V by XL, or simply V square into BL. So therefore you can go for any of the expressions, we are going to get the same one. Whereas S is equal to V into I, or I is called as a V by mod Z, or we can say V square into mod Y. So therefore V square into mod Y. You can go for any of the expression. The capital V is called as the RMS value of the supply voltage, and capital I is called as the RMS value of the supply current. So now we are going to study about the RC parallel circuit behavior to AC source. Means when we are going to connect the resistor and capacitor in parallel across the supply voltage, then we are going to study what is the nature of the power factor, and each and everything we are going to study. So R and C are in parallel, so therefore voltage across R and C is same as the supply voltage. So the current drawn by the resistor is IR of T, and the current drawn by the capacitor is IC of T, and the overall current to the supply voltage source I of T. So therefore I of T is equal to IR of T plus IC of T. So Xc is equal to 1 by omega C, because the capacitance reactance is equal to 1 by omega C. Because these two are going, so now we are going to do some analysis, which is these two are going to cut in parallel. So therefore overall impedance is equal to, let me assume this is Z. So 1 by Z is equal to 1 by R plus 1 by minus JXC. So minus JXC. So if you go for the cross multiplication with respect to J, then we are going to get J by minus J square, which is plus J. So therefore plus J by XC. So 1 by Z is called as the admittance, and 1 by R is called as the conductance, and 1 by XC is called as the susceptance. So therefore Y is equal to G plus J DC. So now I am going to take the voltage as the reference, because it is a parallel combination across the two elements, so both are same. But in a resistor, the voltage across the resistor and the current in the resistor are in phase to each other, so this is IR. But in a capacitor, the current is going to lead the supply voltage by 90 degrees, so this is IC. But if you want to know what is the net current, it is the vector addition of these two vectors, which is I. And if you can see clearly, the angle between the supply voltage and the supply current is called as the power factor angle. So now what I am going to do is simply here, this IR is equal to, call as the IR is equal to V by R, or simply D into G. And similarly IC is equal to V by XC, or simply we can say V into BC. And similarly I is equal to V by mod Z, or simply we can say V into mod Z. So if you cancel out all the V terms, we are going to get mod by BC and G. So these two are the similar triangles, so theta is the same as previous one. So now I am going to multiply the voltage V for each and every side for this triangle. So therefore V into IR is called as the P, whereas V into IC is called as the QC, and V into I is called as the S. So therefore, so by using the Pythagoras theorem, we can say I is equal to under root over IH square plus IC square, and mod Y is equal to under root over G square plus BC square, and S is equal to under root over P square plus QC square. And if you want to know what is the power factor, which is cos theta is equal to adjacent by hypotenuse, which is G by mod Y is equal to IR by I is equal to G by P by S. So always the current is going to lead the supply voltage, so we say it is a leading power factor. So no matter whether you connect the capacitor and resistor in series fashion or in parallel fashion, always the power factor of the circuit is always in leading. Means the current is going to lead the supply voltage. We can say only the resistor is going to consume the active power, but not the capacitor. So P is equal to V square by R, or simply we can say V square into G. So Vi cos theta. And similarly QC is equal to V square by XC. So 1 by X is I and BC. So V square into BC, or you can simply write, which is Vi sin theta. And similarly now here S is equal to V square by mod Z, or simply we can say V square into mod Y, which is V into capital I. So therefore you can go for any of the thing, we are going to get the same result. Where capital V is called as the RMS value of the supply voltage, and capital I is called as the RMS value of the supply current. So now we are going to study about the RLC parallel circuit behavior to AC source. So we are going to study about the RLC parallel circuit behavior to AC source. So what is the nature we are going to study? See, RLC are the parallel elements, and we are going to connect to a supply voltage source. The current drawn by the resistor is IR of T, and the current drawn by the inductor is IL of T, and the current drawn by the capacitor is IC of T. See, the inductor reactance is omega into L, and the capacitor reactance is equal to 1 by omega C, and the overall current drawn is IR of T. So therefore IR of T is equal to I of T is equal to IR of T plus IC of T plus IL of T plus IC of T. So these three are going to cut in parallel. So therefore we can say the net equivalent impedance, let me assume this is Z. 1 by Z is equal to 1 by R plus 1 by J XL or omega L plus 1 by minus J XC means minus J by omega C. So here if you do the cross multiplication with respect to J by J, here you are going to get minus J by XL, and here if you do a cross multiplication with respect to J, we are going to get now plus J by XC. So therefore G plus J into 1 by XL is BL and 1 by XC is BC. So if this simplification we are going to get, and 1 by Z is Y and 1 by R is G. So if you do the simplification we are going to get I is equal to G plus J into BC minus BL, where BC is the susceptance of the capacitance and BL is the susceptance of the inductance. Then what is going to happen? If now suppose if IC is equal to IL, if IC is equal to IL means the overall current is equal to the resistive current. So we simply say it is a unity power factor network. When IC is less than IL means we can say the current in the inductor is very higher. Means the current in the inductor is very higher. So therefore we can say it is a lagging network. When IC is greater than IL means the current in the capacitor is greater than the inductor current. So therefore we say it is a leading network or capacitive network. So now we are going to analyze a special condition when IC is greater than IL. When IC is greater than IL means the current in the capacitor is higher than the current in the inductor. It indicates that it is a capacitive network. So now, as I have already told you, the three elements are connected in parallel. So voltage is the reference vector. So in a resistor, voltage and the resistor are in phase. So this is IR. But in a inductor, the current is going to lag, which is IL. And but in a capacitor, the current is going to lead the voltage, which is IC. I have assumed that IC is greater than IL. So therefore, overall vector addition will become, which is IC minus IL in this direction. So therefore now, if I add these two vectors, we are going to get the overall supply current. So you can see clearly the overall current is leading the supply voltage. It indicates that it is a capacitive network. So therefore this is angle theta. So now here I am going to do IR is equal to V by R, or simply we can say V into G, and similarly IC is equal to V by XC, or simply we can say V into BC minus V into VL, and similarly I is equal to V by Z, V by mod Z, or simply we can say V into mod by. So if you cancel all the V terms, we are going to get G, BC minus BL and mod by. So these two are the similar triangles. So till the angle is here theta. Whereas if you are going to multiply by an extra factor V for each and every side, we are going to get V into IL is P, VIC minus VIL is QC minus QL, and V into I is called as the S. So by using the Pythagoras theorem, we can know that I is equal to under root over IR square plus IEC minus IL whole square, whereas mod Y is equal to under root over G square plus BC minus BL whole square, whereas S is equal to under root over P square plus QC minus QL whole square. So now, if I want to know what is the power factor which is adjacent by hypotenuse, which is G by mod Y or IR by I by P by S. So all these things are, current is going to lead always the supply voltage. So we say it is a leading network. See, it is a leading network. I already told you here P, the active power is going to consume only by the resistor but not the capacitor or inductor. So therefore P is equal to V square by R, or we can simply say with it is V square into G, which is also equal to VI into cos theta. Whereas Q is C is equal to, so QC is equal to V square by XC, or simply we can say V square into BC, and QL is equal to V square by XL, or simply we can say V square into BL. But if you are going to go for the each and everything which is QC minus QL, so QC minus QL is equal to everything here, QC minus QL is equal to, if you take V square common, which is V square of BC minus VL, it is equal to VI sin theta. This is equal to VI sin theta. So this is the overall reactive power. So VI sin theta. So but V is equal to V square by mod Z, or simply we can say V square into mod Y, which is equal to V into I, where capital V is the RMS value of the supply voltage and capital A is the RMS value of the supply current. Now we are going to analyze some beautiful circuit. See, so this is some circuit which is going to contain two branches. This is R1L1 and this is R2C. So inductive and this is capacitive. So therefore we are going to connect an AC RMS voltage of V. So it is going to draw some current of, and it is going to send some current of I. So I1 is the current which is going to flow through the R1L1, whereas I2 is the current which is flowing through R2 and C. So now I am going to analyze this circuit. Here I1 is equal to voltage by overall impedance, which is I1 is equal to V by R1 plus JXL. So therefore, if you are going to write, or if you are going to rationalize with respect to R1 minus JXL by R1 minus JXL, it is nothing but V by Z1. So therefore, we are going to call it as the overall voltage by overall impedance. So if you do the rationalization with respect to R1 minus JXL by R1 minus JXL, you are going to get finally, which is V part is going to get cancelled. So therefore, simply you are going to get 1 by Z1 is called as the Y1. So Y1 is equal to R1 by R1 square plus XL square minus J into XL by R1 square plus XL square. So simply you are going to call, this is called as the admittance of the branch 1. So I am going to make this as the G1 and I am going to assume this as BL. So therefore, Y1 is equal to G1 minus JBL. So just we did the rationalization with respect to R1 minus JXL and R1 minus JXL. So we got the expression which is Y1 is equal to G1 minus JBL. Similarly, if you want to find what is the current through the branch of containing R2 and C, then it will become I2 is equal to V by R2 minus JXC. So if you do the rationalization with respect to R2 plus JXA by R2 plus JXA, it is equal to voltage by overall impedance. So VV is going to get cancelled. So 1 by Z2 is called as a Y2. So Y2 is equal to, if you do the multiplication, then you are going to get finally R2 by R2 square plus XC square plus J of XC by RC square, R2 square plus XC square. So I am going to assume this is G2 and this is BC. So therefore Y2 is equal to G2 plus JBC. But if you apply the KCL at that node, the overall current is equal to summation of the individual currents, which is current I is equal to I1 plus I2. So but the voltage is very same, or simply we can say V by Z equivalent is equal to V by Z1 plus V by Z2. But 1 by Z equivalent is Y equivalent and 1 by Z1 is Y1 and 1 by Z2 is Y2. So therefore V into Y equivalent is equal to V into Y1 plus V into Y2. So V is a common part in each and every term. So we are going to cancel the common part V and we are going to get finally Y equivalent is equal to Y1 plus Y2. So finally we are going to get Y equivalent is equal to Y1 plus Y2. So therefore, if you know the value of Y1 and you know the value of Y2, just do the addition. We are going to get finally Y equivalent is equal to G1 plus G2 plus G of BC minus BL. So this is called as the equivalent admittance of these two branches, which is G1 plus G2 plus of J into BC minus BL. So now we will discuss the series RL circuit. So this is a resistor and is an inductor. So the voltage across the resistor is VR of T and the voltage across the inductor is VL of T. So therefore, the current through this branch is I of T and the supply voltage is V of T of RMS voltage. So therefore, V of T is called as the instantaneous voltage of the AC source. So therefore, we can say clearly here, by using the KVL, we can say that VR plus VL is bar is equal to V bar. So therefore, these are the vector quantities. So therefore, we can say whenever there are AC quantities, we have to go for the vector addition. But if you are going for the DC analysis, we have to go for the algebraic sum. So therefore, V bar is equal to VR bar plus VL bar. So VR bar is equal to I bar into R, whereas VL bar is equal to I bar into JXL. So therefore, here the current is same in both the resistor and inductor. So I am going to take the current as the reference phasor. So if you are going to take current as a reference phasor, you can say clearly in a resistor, the current in the resistor and the voltage across the resistor are in phase of each other. So therefore, because of this is a VR. But in an inductor, the current is going to lag the voltage across the inductor by 90 degrees. So therefore, because of that reason, this is called as the VL. So if you take the overall addition of these two vectors, we are going to get the overall vector, which is called as the V. So this is called as the source voltage. So therefore, we can say where phi is the angle between the supply voltage and the supply current. So this we are going to call it as the power factor angle. So now tan phi is equal to opposite by adjacent, which is VL by VR is equal to I into XL by VR is equal to I into R. So II is going to get cancelled. So we are going to get XL by R. Or similarly, in the similar triangles also I have told you this is Q and this is P and this is S. So therefore, tan phi is equal to Q by P. So simply we can say that here tan phi is equal to Q by P. So therefore, if you want to know what is the cos factor, which is cos phi, which is the adjacent by hypotenuse, which is VR by V. So as the current is going to lag the supply voltage, we say it is a lagging network, or we can say it is a inductive circuit. So if you want to know what is the power consumed by the resistor, because only a resistor is going to consume the power but not the inductor. So therefore, whatever the average power sent by the source is equal to the average power consumed by the resistor. So therefore, average power consumed by the resistor is equal to RMS value of the current whole square times the resistor, or simply it is equal to V into I into cos theta, where V is called as the RMS value of the supply voltage and I is called as the RMS value of the supply current, and theta is the angle between the supply voltage and the supply current. So here V is called as the supply voltage of RMS value, whereas if you want to know what is the RMS value of the voltage across the resistor, which is IRMS into R. So this we are going to call it as the RMS voltage drop across the resistor. So now we are going to learn about the RC circuit. So you can see clearly this is a series RC circuit. So we are going to apply a voltage source of V of t, and the current is flowing through resistor and capacitor is I of t. So across R the voltage drop is VR of t, and across capacitor the voltage drop is Vc of t. So by whenever there are AC quantities, we have to go for the vector addition, which is supply voltage V bar is equal to VR bar plus Vc bar. So this is the vector voltage of the supply voltage, and this is the vector voltage of the resistor, and this is the vector voltage across the capacitor. So therefore V bar is equal to VR bar plus Vc bar. So VR bar is equal to R into I bar. So therefore VR bar is equal to R into I bar, whereas Vc bar is equal to I bar into minus j Xa. So in this the current is same in the resistor and the capacitor, so therefore we are going to take the current as a reference vector. So in a resistor the current and the voltage will be same, so therefore this is VR. But in a capacitor the current is going to lead the voltage across the capacitor by 90 degrees. So because of that reason this is going to lag, Vc is going to lag the current by 90 degree. So if you want the overall voltage, just do the vector addition. So this is called as the supply voltage. So therefore V bar is equal to VR bar plus Vc bar. And if you want to know what is the tan phi, is equal to opposite by adjacent, which is Vc by VR. But Vc is equal to I into Xc and VR is equal to I into R. So I and I is common part between the two terms, so they are going to get cancelled. So finally Xc by R, Xc is equal to 1 by omega C. So therefore finally you are going to get the expression as 1 by omega RC is equal to, this is the reactive power and this is the active power, which is a Q by P. So always you can see clearly the current is going to lead the voltage. So we are going to say this network as a capacitive network or a leading network. So if you want to find what is the power factor of this the circuit, which is adjacent by hypotenuse, which is VR by V, so we can say it is a leading network. So here now we are going to learn about the series RLC circuit. So this is a resistor, inductor and capacitor. The voltage across the resistor is VR of t, and the voltage across the inductor is VL of t, and the voltage across the capacitor is Vc of t. So we are going to apply a source voltage of V of t. So by using the vector addition, V bar is equal to VR bar plus VL bar plus Vc bar. So VR bar is equal to, here current is I bar. So I bar into, so this is the current I bar which is flowing in this circuit. So therefore VR bar is equal to I bar into R, and VL bar is equal to I bar into JXL, and Vc bar is equal to I bar into minus j Xc. So now here, see, suppose if the voltage across the inductor is greater than the voltage across the capacitor, now we are going to study. So see, the first thing is, here I want to draw the phasor diagram of the circuit. As the current is same in each and every part, then we are going to say it is a, we are going to take current as a reference. But in a resistor, the voltage and the current are in phase, so this is VR. But in a inductor, we can say the current is going to lag, so therefore this is VL, and in a capacitor the current is going to lead, so therefore this is called Vc. So I am going to assume that VL bar is greater than Vc bar, only the magnitude part we are going to take. So therefore I into XL is greater than I into XC. So I is a common part, we are going to cancel it. So we are going to get, if XL is greater than XC, then definitely VL bar is greater than Vc. So because of this upper part is greater than the down part, so therefore overall vector will be in the upward part, which is VL bar minus Vc. So if you do the vector addition of these two quantities, we are going to get, this is the supply voltage. So you can see clearly supply voltage is going to lead the current. So therefore we say it is a leading, or we can say lagging network, because the current is going to lag the voltage. We say it is a lagging network. So therefore we can say, if you want to know what is the tan phi, which is the opposite by adjacent, which is VL minus Vc by VR, as VL is equal to I into XL and Vc is equal to I into Xc and VR is equal to I into R. So I is a common part, and each and every term we are going to get XL minus Xc by R. And similarly, if you want to know what is the cos phi power factor of this circuit, which is adjacent by hypotenuse, which is VR by V. So this is basically a lagging network, because the current is going to get lagging the supply voltage. Suppose if Vc bar is greater than VL bar, means if the downward vector is higher than the upward vector, means the overall vector addition will become in the downward direction, which is Vc minus VL. So if we do the vector addition of these two vectors, we are going to get the overall supply voltage. or simply we can say VC is equal to I into XC and VL is equal to I into XL. As I is a common part, we can cancel it. We are going to get X is greater than XL. So definitely we can say now the current is going to lead the supply voltage. So we say this is said to be a leading network or leading circuit. So therefore tan phi is equal to opposite by adjacent, which is VC minus VL by VR. So cos phi is equal to adjacent by hypotenuse, which is VR by V. So we can say the current is going to lead the supply voltage. So we say this is said to be a leading circuit. So therefore, so we have studied about the lagging and also about the leading. Suppose if the last case is, suppose if VL bar is equal to VC, then what is going to happen? VL bar is equal to I into XL and VC bar is equal to I into XC. So IA is going to get cancelled. Then we are going to get XL is equal to XC. Means if the upper vector is equal to downward vector, so there will be net 0 in the upward and downward direction. So therefore we can say overall vector is equal to the voltage drop across the resistance. So whatever the supply voltage, but supply voltage is going to drop totally across the resistor. Or simply we can say now cos phi, we can say simply the supply voltage and the supply current are in phase. So therefore the power factor angle is equal to 0. So cos phi is equal to 1. So therefore we say it is a unity power factor circuit. Now we are going to study about the parallel RL circuit. So this is a parallel RL circuit. So we are going to connect a current source of I of t to this parallel source. Then what we are going to get is here the voltage drop, the voltage across the R and L are same because they are current in parallel. So let me assume this is V of t and the current through the resistor is IR of t and the current through the inductor is IL of t. Then the overall current, supply current is I of t. So now I am going to take voltage as a difference vector because it is same for both the elements. Whereas in the resistor, the voltage and resistor current are going to be in same phase. So therefore this is IR. Whereas in an inductor, the current is going to lag the voltage by 90 degrees. So therefore this is IL. So if you do the vector addition of these two vectors, we are going to get the overall supply current, which is I. So, and if you want to know what is the angle between the supply voltage and supply current, is power factor angle, which is phi. So therefore you can see clearly the current is going to lag the supply voltage by phi, or simply it indicates that here this is a lagging. So therefore whether you connect the resistor and inductor in series or in parallel, the overall circuit will be always inductive in nature. So therefore this will become inductive circuit. So if you want to know what is the tan phi, which is a ratio of the opposite by adjacent, which is IL by IR, and if you want to know what is the cos power factor angle or cos phi power factor of the circuit, which is adjacent by hypotenuse, which is IR by I, it is basically lagging circuit because the current is going to lag the supply voltage. So now we are going to learn about the parallel RLC circuit. See, parallel RC circuit now we are going to study. See, basically it is a parallel RC circuit. Here we are going to connect a current source of I of t. See, as these are in parallel, the voltage will be same, which is V of t, and the current through the resistor is IR of t, and the current through the capacitor is IC of t. So you can see clearly that the supply current is equal to the vector we can say the vector addition of these two currents. So therefore we can say clearly, as the voltage is same between the resistor and capacitor, so we are going to take voltage as a difference vector. So therefore in a resistor, the voltage and current are in phase, so this is IR, but in a capacitor, the current is going to lead the voltage. So therefore this is IC. So if you do the vector addition of these two vectors, we are going to get the overall supply current of I. And the power factor angle, the angle is the power factor, means the voltage. So you can see clearly the current is going to lead the supply voltage by an angle of phi. That angle we are going to call it as the power factor angle. So if you want to know what is that tan phi, so tan phi is equal to opposite by adjacent, which is IC by IR, whereas cos phi is equal to adjacent by hypotenuse, which is IR by I. So you can see clearly the current is going to lead the supply voltage. It indicates that it is a leading circuit. So no matter whether you keep the resistor and capacitor in series or in parallel, definitely we can say that the overall circuit will always behave like a capacitive circuit. So now we are going to study about the parallel RLC circuit. So this is the resistor, inductor and capacitor. And see, we are going to connect a current source, supply source of I of t. And as these three elements are in parallel, we can say the voltage is same across each and every element, which is V of t. And the current through the resistor is IR of t, and the current through the inductor is IL of t, and the current through the capacitor is IC of t. Then the supply current is equal to IR bar plus IL bar plus IC bar. So now I am going to do the analysis of this circuit. So therefore, as the voltage is same for each and every element, so we are going to take the voltage has a difference phasor. In a resistor, the current and the voltage are in same phase. But in an inductor, the current is going to lag. But in a capacitor, the current is going to leak in this fashion. So now I am going to assume a special case, which is when IL is greater than IC. When IL is greater than IC means the overall vector will be in the downward direction of IL minus IC. So if you do the vectorization of these two vectors, we are going to get this is I. So you can see clearly the current I is going to lag the supply voltage by an angle of phi. This we are going to call it as a power factor angle. So simply we can say that tan phi is equal to ratio of opposite by adjacent, which is IL minus IC by IR, whereas cos phi is equal to adjacent by hypotenuse, which is IR by I. So always the current is going to lag. So therefore this is the lagging power factor. Or simply one of the important point is here. See, if the current in the inductor is greater than the current in the capacitor, it indicates that the circuit is said to be a lagging circuit, because we can see simply from this phasor diagram also the current is going to get lagged. Suppose if IC is greater than IL, means here the overall vector will be in the upward direction, which is IC minus IL. So if you do the vectorization of these two vectors, we are going to get the overall summation of I, supply current. So therefore we can see clearly the supply current is going to lead the supply voltage by an angle of phi. So this is said to be a leading network. And if you want to know what is the value of tan phi, which is IC minus IL by IR, whereas cos phi is equal to IR by I. So basically this is said to be a leading circuit. If suppose the special case is if IC is equal to IL, then overall vector in the upward direction is 0, then the only vector which we are going to get remaining is IR. So therefore supply current is equal to IR. So we can say the supply voltage and the supply current are in phase with each other. So definitely we can say the power factor angle is equal to 0. So cos phi is equal to 1. So we can say it is a unity power factor circuit, because the circuit is now going to behave exactly like a purely resistive circuit. So now we are going to study some of the important concepts, which is suppose if RLC circuit is excited by DC source. See what is going to happen if you are going to excite RLC circuit by a DC source of voltage V. Then I am going to assume that the current in the circuit is I of t. So now I am going to do the analysis of the circuit, which is the supply voltage is equal to the voltage drop across the resistor is R into I of t, and the voltage drop across the inductor is L into di of t by dt, and the voltage drop across the capacitor is 1 by C into the relation of minus infinity to t I of t dt. So now I am going to do the derivative with respect to time in the LHS and also in the RHS. Then I am going to get dv by dt is equal to L into d square I by dt square plus R into di of t by dt, plus here this will become now I of t by C. So this dv by dt is called as the differentiation of any constant value. We are going to get 0. So therefore this part will be 0, and I am going to divide by L on the left. So now I am going to divide by L in the LHS and also in RHS. We are going to get finally d square I of t by dt square plus R by L di of t by dt plus I of t by LC is equal to 0. So now I am going to take I of t as a common, and I am going to assume d by dt is equal to d. So with the help of this we are going to get d square plus R by L d plus 1 by LC is equal to 0. So this is in the standard formation of the second order, which is like a square plus 2 zeta omega ns plus omega n square is equal to 0, where zeta we are going to call it as the damping ratio and omega n is called as the natural frequency. So now by comparing these two equations, we are going to get omega n is equal to 1 by under root over LC, whereas zeta is equal to R by 2 into under root over C by L. See, this is a very much important concept. So therefore for a series RLC circuit, always the natural frequency is equal to 1 by under root over LC, whereas zeta is equal to R by 2 into under root over C by L. It's a very important formula. See, basically a lot of questions are asked on this concept, so I recommend you to remember this formula, which is omega n is equal to 1 by under root over LC, whereas zeta is equal to R by 2 into under root over C by L. So now we are going to study about the power calculations. Suppose if the supply voltage V of t is equal to Vm sin omega t plus theta V, so then RMS values of this voltage is Vm by root 2. And if the current through this voltage source I of t is equal to Im sin of omega t plus theta I, then the RMS value of this current is equal to Im by root 2. Then if you want to know what is the instantaneous power, which is V of t into I of t, so if you do these things and if you do the simplification, finally we are going to get P of t is equal to Vrms into Irms into cos of theta V minus theta I minus Vrms Irms cos of 2 omega t plus theta V plus theta I. But if you want to know what is the average power, see, this is a DC component, whereas this is a cosine wave. So therefore if you do the integration over one time period, definitely this value will become 0, because integration of cos function over one time period is always going to give you 0. So only this component is going to get remain. So therefore P average is equal to Vrms Irms for cos of theta v minus theta I. See, now I am going to make this time domain into a polar format, which is Vrms at an angle of theta v, and this is Irms at an angle of theta I. So if you draw a phasor diagram, we are going to get the voltage vector Vrms at an angle of theta v and Irms at an angle of theta I. I have assumed that theta v is greater than the theta I. Then if you want to know what is the complex power, the complex power expression is Vrms bar into Irms bar whole conjugate. So this is the conjugate only for the current value. So Vrms bar is equal to Vrms at an angle of theta v, and the Irms bar is nothing but Irms at an angle of theta I whole conjugate. Then we are going to get finally Vrms into Irms theta v minus theta I. So if you do into split into two parts, like R at an angle of theta is equal to, we are going to get R cos theta plus J R sin theta. So with the help of that, we are going to get Vrms Irms cos of theta v minus theta I is called as the active power, Vrms Irms sin of theta v minus theta I. So therefore this we are going to call it as the reactive power. So only thing is that theta v minus theta I indicates that the angle between the voltage and the current RMS values. So simply we can say theta v minus theta is called as the angle between the Vrms and the Irms. Suppose in the question they are given V of t as this expression and I of t as the expression, and they are asking what is the average power and everything they are going to ask. Suppose V of t is equal to Vm1 sin omega t plus Vm2 sin 2 omega t plus Vm3 sin 3 omega t, and it goes on. And similarly I of t is equal to Im1 sin of omega t minus phi 1 plus Im2 sin of 2 omega t minus phi 2 plus Im3 sin of 3 omega t minus phi 3, and it goes on. So in the question they are asking basically what is the average power. If they are going to ask the average power, the simple way is take only the same frequency terms. If this is omega, this is also omega. If this is 2 omega, and this is also 2 omega. If this is 3 omega, and this is also 3 omega. Means take only the similar frequency terms. So therefore this is Vrms into Irms into cos of angle between these two things, which is phi 1. And similarly Vrms into Irms into cos of angle between these two terms, which is phi 2. And similarly Vrms into Irms into cos of angle between these two terms, which is cos phi 3, and it goes on. So therefore here we are going to get the average power expression. But if you want to know what is the RMS value of this voltage, then it is under root over RMS value of the first signal whole square plus RMS value of the second signal whole square plus RMS value of the third signal whole square plus, and it goes on. Always here this omega, 2 omega, 3 omega are different. Then only we have to use this formula. Otherwise we don't have to use this formula. And IRMS is equal to under root over RMS value of the first signal whole square plus RMS value of the second signal whole square plus RMS value of the third signal whole square plus, and it goes on. So we have to take the overall square root. So by this we are going to get the overall RMS value of the current I of t. For average power is equal to Vrms into Irms into cos of phi, where phi is the angle between the V of t and the I of t. So this is called as a phase difference between the voltage and the current. So therefore, see, we know the value of P average, we also know the value of Vrms, and we also know the value of Irms. So from this we can easily find the cos factor, we can see the power factor of this circuit also we can figure out, which is cos phi. So what is going to happen for different loads? For resistive loads, the supply voltage and the supply current, they will be in phase. So therefore theta v is equal to theta I. So simply we can say P is equal to always positive, whereas Q is equal to 0. You can apply that formula, which is P is equal to Vrms Irms cos of theta v minus theta I. So it will become cos 0 is equal to 1, whereas sin 0 is equal to 0. So because of that, the resistor is going to consume only the average power, but not the reactive power. So always the average reactive power will be always going to 0 for a resistor. Whereas for the inductor, here theta v minus theta is equal to 90 degree. So therefore we can say simply here cos 90 is equal to 0. Because of that, P average is equal to 0, whereas Q is equal to sin 90. So sin 90 is again positive. So because of that, we are going to get some positive value, we are going to get like non-zero. So therefore we are going to call it as the average power. It is going to absorb. So therefore the inductor is going to absorb an average reactive power. It is not going to absorb any average active power. So therefore simply we can say the inductor is going to absorb an active, or simply we can say it is going to absorb an average reactive power only. Whereas for capacitor, we can say clearly theta I minus theta v is equal to 90. So therefore if you take minus part here, it's still you are going to get cos of minus 90 is again we are going to get 0. So because of t is equal to 0, but sine of minus 90 will become minus 1, so therefore it has become negative. So therefore simply we can say the average reactive power is always going to negative, means it is going to deliver and average reactive power. So we can say simply that here resistor is going to absorb and average active power, but it can't absorb any average reactive power. Whereas for inductor, it doesn't absorb any average active power, but it only absorbs an average reactive power. For a capacitor, the average active power absorption is 0, whereas it is going to deliver an average reactive power. So this is the meaning of all these three things. This is called as this vector is going to represent the average active power, and this is the average reactive power, and this is the average capacitor reactive power. So therefore, average active power, average inductive reactive power, and average capacitor reactive power. So now we are going to learn about the quality factor. See, quality factor is equal to the expression of the quality factor is equal to 2 pi into maximum energy stored by energy dissipated in one cycle. So the expression of the quality factor is equal to 2 pi into maximum energy stored by energy dissipated in one cycle. Means in one cycle the maximum energy stored by the energy dissipated in one cycle, it is a ratio of these things into 2 pi is called as the quality factor, or simply we can say it is equal to ratio of the reactive power by the active power, or we can say it is a power dissipated or active power. So therefore Q is equal to ratio of the reactive power by the power dissipated or active power. So always dissipation factor means it is a reciprocal of the quality factor. So therefore dissipation factor is equal to 1 by the quality factor. So now we are going to learn some important formulas. See, for a resistor, we can say clearly it is going to absorb only active power but no reactive power. So therefore Q is equal to 0. So quality factor is equal to ratio of the reactive power by active power. As the reactive power is equal to 0, 0 by any positive value is again 0. Whereas for inductor, we can say the quality factor is equal to ratio of the reactive power by active power. But for inductor, the active power consumption is 0, but the reactive power consumption is positive. So therefore positive by 0 is again plus infinity. Whereas for a capacitor, we can say it is a ratio of the reactive power by the active power, but it is not going to absorb any active power. It is going to deliver only some reactive power. So because of that, we can say anything by 0 is again plus infinity. Whereas for a RL circuit, or we can say for RL circuit of series fashion, then quality factor is equal to XL by R. Similarly, for RC circuit of series fashion, the quality factor is equal to XC by R. And similarly, for RLC series circuit, the quality factor is equal to XL by R is equal to XC by R is equal to. So therefore, you are going to get here XL is equal to XC. So with the help of that, you are going to get some expression of omega. So if you substitute that, we are going to get finally 1 by R into under root over L by C is called as the quality factor of the series RLC circuit, which is XL by R is equal to XC by R is equal to 1 by R into under root over L by C. So if you want to know what is the quality factor of a parallel RL circuit, it's the reverse of the series, which is R by XL. So the quality factor of a parallel RC circuit is the reciprocal of the series RL circuit. So therefore we are RC circuit, we are going to get here R by XC. And similarly, if you want to know what is the quality factor of a parallel RLC circuit, these are the reciprocal of a series RLC circuit. So therefore we are going to get R by XL is equal to R by XC is equal to R into under root over C by L. So everything is the reciprocal of the previous ones. So by this manner we can easily figure out the quality factor of the circuits. So now we are going to study some important points on the quality factor. For occurrence of resonance in any system, two energies are required. See, in order to for a resonance in a circuit, definitely two energy storage elements are required. One is inductive and the other is capacitive. Then only we can say the resonance is going to occur. If there are two energy storage elements, then only we are going to get the resonance. Otherwise, we are not going to get the resonance. In the electric circuit, inductor is having energy in the form of magnetic field and the capacitor is having energy in the form of electric field. Yes, see, always the inductor is going to have the energy in the form of the magnetic field, whereas the capacitor is going to have the energy in terms of the electric field. When these two energies are present at one particular frequency, wide variations are present in the system. So what is going to happen is, at one particular frequency, the overall circuit is going to become a resistive circuit. So because of that, we are going to say it as a resonance circuit. So therefore we can say simply here, at one particular frequency, then this inductive, this oral circuit is going to become like a resistive circuit. A circuit is said to be in resonance when the source current is in phase with the source voltage. See, a circuit is said to be in resonance only when the supply voltage and the supply current are in phase with each other. There is no phase difference. Then only we can say that circuit is a purely resistive, and this condition we are going to call it as the circuit is in resonance. Quality factor relates the maximum energy stored to be in the circuit to the power dissipation per cycle. I have already told you the quality factor is equal to 2 pi into maximum energy stored by the power dissipation in one cycle. That is called as the quality factor. Quality factor influences on the designing of bandwidth and selectivity of the circuit. See, because of quality factor, we can choose the bandwidth and also selectivity of the circuit. See, because of bandwidth and selectivity only, we are going to get the quality factor. To obtain high efficiency network is designed with high quality factor. So if you want high efficiency, it is better to design with any circuit with highest amount of quality factor. So more is the quality factor, more is the efficiency. To obtain high bandwidth network is designed with low quality factor. So therefore we can simply say that if you want, because these both are inversely proportional to each other. So these both are, the bandwidth and the quality factor are inversely proportional to each other. So therefore, if the bandwidth is very, very low, so we can say the bandwidth is very, very low, then the quality factor is very high. But if the bandwidth is very, very high, then we can say the quality factor will be very, very low. So therefore, we can say simply here, if you want higher bandwidth, then the quality factor is very less. If you want higher quality factor, the bandwidth should be always less. When the curve is drawn between the current and when the graph is drawn with the current and the frequency, then it is called as a resonance curve. Means at each and every frequency we are going to see what is the nature of the current magnitude value we are going to see. That graph we are going to call it as the resonance curve. So that graph we are going to call it as the resonance curve. So bandwidth is the range of frequencies on either side of the resonance frequency where the current falls from the maximum to the 70.7% of the maximum. So basically the bandwidth is nothing but it is a just in the both sides at the resonance frequency where the current is going to reach the 1 by root 2 times the maximum value, or we can say simply, or also we can call it as the 50% of the power is going to get dissipated. So therefore simply here at those points in the bandwidth, the current will be 1 by root 2 times of the maximum, or 70.7% of the maximum current. At that points only we are going to get half of the maximum power. So in series RLC circuit at resonance, VR is equal to Vs RMS. I have already told you in a series RLC circuit at the resonance, VL is equal to Vc. So because of that, supply voltage is equal to voltage across the resistor. So therefore this is called as the RMS value of the voltage across the resistor is equal to RMS value of the source voltage. And this maximum voltage across the resistor and the current at resonance is I is equal to Vs RMS by Z minimum is equal to R. See, because now there is a huge amount of voltage. So as the voltage is very, very high, it is equal to supply voltage at resonance. Then I is equal to V by Z. But Z is a very, very minimum because it is a purely resistor. So because of that, this overall ratio will be very higher. So therefore at resonance in series RLC circuit, the resistor or the circuit is impedance means less, the circuit is resistor means less amount of impedance. So overall ratio is very, very higher at resonance condition in a series RLC circuit. In series resonance RLC circuit, when Q is greater than 10, the curve between the current and frequency is symmetrical between if not, otherwise not. See, it's a very special condition in series resonance RLC circuit. When quality factor is greater than 10, the curve between the current and frequency is symmetrical between if not, otherwise not. This is a very important point here. See, this is a special condition only when the quality factor is greater than 10. When the quality factor is greater than 10, then only we can say that the curve is symmetrical. The curve is symmetrical with respect to the resonant frequency. Otherwise, that is not the case. Series RLC resonance circuit is also called as the acceptor circuit. So, series RLC resonance circuit is also called as the acceptor circuit, whereas parallel RLC circuit is also called as the rejector circuit. So therefore, series RLC circuit is also called as the acceptor circuit, whereas the parallel RLC resonance circuit is also called as the rejector circuit. At resonance, power factor is equal to 1 because as the supply voltage and the supply current are in phase with each other. So power factor angle is equal to 0. So therefore power factor is equal to 1. It indicates that it is a purely resistive circuit, or imaginary part of impedance and admittance are ideally 0. So therefore we can say at resistance the imaginary part of impedance and the imaginary part of admittance are purely 0. Then only we can say the circuit is said to be a purely resistive. So therefore the supply voltage and the supply current are in phase with each other. This condition we are going to call it as the resonance condition. So here always the quality factor and the bandwidth, the relation is, it is inversely proportional. So quality factor is inversely proportional to the bandwidth. For any circuit this is perfectly correct. So no matter whatever the circuit, always the quality factor and the bandwidth are inversely proportional to each other. See, for any circuit only I have already told you, which is Y equivalent is equal to G equivalent plus of BL equivalent minus BC equivalent. So this is the equation just now we have learned in the previous concept only. So therefore at resonance definitely the imaginary part should be equal to 0. It indicates that BL equivalent is equal to BC equivalent. So for a practical inductor, see generally a practical inductor is going to have a small amount of capacitance. So there will be a resistance, there will be an inductance, there will be a small amount of capacitance. But for an ideal inductor, there will be no resistance and no capacitance. But for a practical inductor, definitely there will be a small amount of resistance and capacitance with the help of, and also inductor is going to be present. So for a practical inductor, there is a possibility of self-resonance at high frequency. So generally inductor is operated at normal low frequencies. Suppose if you are going to operate the inductor at very huge frequency, then there may be a chance of self-resonance. So because of that, resistor, inductor and capacitor is going to present. So therefore at high frequency there is a possibility of self-resonance, means huge current can flow. So because of that reason only we are going to operate the inductor at very normal low frequencies but not at huge high frequencies. So for practical inductor there is a possibility of self-resonance at high frequency. So generally inductor is operated at normal low frequencies but not at higher frequencies. So now we are going to learn about the series resonance. So this is the resistor, this is an inductor and this is the capacitor. So we are going to connect all these three things in a series manner, and the supply voltage is V. V is called as the RMS value of the supply voltage and I is the RMS value of the supply current. So now I want to know what is the overall impedance, which is that is equal to R plus J XL minus J XC. So that is equal to R plus J, XL is equal to omega L and XC is equal to 1 by omega C. So if you substitute here we are going to get this expression. Say I want to know only the magnitude part of the impedance, which is under root over R square plus omega L minus 1 by omega C whole square. See now at resonance I have already told you the circuit should be purely inductive, it is purely resistive, so therefore the inductive part should be always equal to 0. So therefore if you equate this part to 0, then we are going to get Z is equal to R. So therefore it indicates that XL is equal to XC. Then only we are going to get this part as 0. So therefore omega naught L is equal to 1 by omega naught C at a one particular frequency, which is omega naught. So omega naught L is equal to 1 by omega naught C. So if it is the simplification, we are going to get omega naught is equal to 1 by under root over LC. Means at this angular frequency only we are going to get the inductive part is equal to the capacitive part, and then we are going to get the circuit as purely resistive. That we are going to call it as the resonant frequency of omega naught. If you are going to draw the phasor diagram at resonance condition, as it is a series RLC circuit, so current is same for each and every element. So we are going to take the current as the reference vector. So therefore we can say clearly in a resistor, the voltage across the resistor and the current are in phase with each other. So therefore this is a VR. But in a inductor, we can say simply the current is going to lag the voltage. In a capacitor, the current is going to lead across the voltage across the capacitor. So because of that, but I have already told you here at resonance XL is equal to XC. So therefore VC is equal to VL. So because of that reason only these two components are going to be equal. So overall vector in the upward direction is 0. So therefore overall supply voltage is equal to the voltage across the resistor. So therefore VR is equal to V. But if you want to know what is a VC and VL, so VC is equal to VL, but VC is equal to I into XC, but I is equal to V by R. So therefore V by R, because V by Z is nothing but V by R into XC. So now XC by R is called as a quality factor. So therefore we are going to get VC is equal to Q into V. And similarly VL is equal to I into XL, but I is equal to V by R into XL. So therefore V into XL by R. So XL by R is called as a quality factor. So we are going to get Q into V. So at resonance condition, VR is equal to supply voltage, VL is equal to VC is equal to Q into supply voltage. So these are some of the important formulas. So now I am going to draw the graph between the magnitude of the impedance with respect to frequency. So magnitude of impedance is equal to under root over r square plus omega L minus 1 by omega c whole square. I am going to change the value of omega and then I am going to draw the graph. Then you can see clearly as omega is going to change from 0, we are going to get the graph is going to get decay. And after omega naught, after omega naught, it is going to increase again. So therefore you can see clearly here up to omega naught, the graph is going to decay, and after omega naught, the impedance is going to again increase. So therefore we can see clearly at omega naught, the impedance is very less, or we can say it is a minimum value. So therefore at omega naught, the impedance value is equal to r. So this we are going to call as a minimum impedance. And you can see clearly here before omega naught, here XL is equal to omega L and XC is equal to 1 by omega C. So because of this measure only we can say here XC is greater than the XL. So therefore because of that reason we say it is a capacitive circuit. So for 0 to omega naught, the circuit is purely capacitive, but at omega naught the circuit is purely resistive. But after omega naught, XL is greater than XC. So because XL is always going to get increased, but XC is going to 1 by omega C is going to get decreased. So because of that nature we can say here the inductive part is higher than the capacitive part. So because of that reason we say it is a inductive circuit. So therefore this is lagging circuit. This is a leading circuit. I see unity power factor, and this is a lagging circuit. Leading, unity power factor, and lagging. Here these are the two bandwidth points, or we can say here cutoff frequencies, which are the omega 1 and the omega 2. So at these frequencies the power factor is equal to 0.707 or 1 by root 2. So here at this region the power factor is 1 by root 2. We can say it is a leading, whereas here power factor is equal to 0.707 lagging. And also at these frequencies the overall impedance value is equal to the magnitude of the impedance will be root 2 into r. Magnitude of the current with respect to omega, I am going to draw the graph. So you can see clearly here for 0 to omega naught, the impedance is going to decay. It indicates that the current will be increasing. But at omega naught, we can say the impedance is minimum, so therefore current will be maximum. And after omega naught, the impedance is going to get increased again, so therefore current should decay. So this is a graph we are going to get with respect to current and the omega. Only the magnitude of the current we are going to take. So therefore simply we can say at this is called as the resonant frequencies. This is a W1 and this is a W2. At these frequencies we can say simply if this is Imax current, this will be 1 by root 2 into Imax. Means if this is the maximum power, at this instance the power will be half of the maximum. So therefore these are called as the bandwidth. So this region total is called as the bandwidth. So this is called as a bandwidth. Means you have to operate only in this range, but not more than this and less than this. So if you want to know what is the value of this omega 1, the formula is minus r by 2l plus under root over r by 2l whole square plus 1 by LC. And similarly omega 2 is equal to r by 2l plus under root over r by 2l whole square plus 1 by LC. These are the very important formula, which is omega 1 is equal to minus r by 2l plus under root over r by 2l whole square plus 1 by LC. And omega 2 is equal to r by 2l plus under root over r by 2l whole square plus 1 by LC. So if you want to know what is the bandwidth, which is omega 2 minus omega 1. So if you solve this one, we are going to get simply 2r by 2l is called as the r by l. So therefore this we are going to get r by l. So these are basically radians per second unit. So therefore this is radians per second. But if you want in terms of hertz, which is f2 minus f1 is equal to r by 2 pi l. So this is in terms of the hertz. Whereas the relation between the resonant frequencies and the cutoff frequencies, which is omega naught is equal to under root over omega 1 into omega naught. Or simply we can also call it as this geometric mean. So therefore the omega naught is a geometric mean of the cutoff frequencies. So therefore omega naught is equal to under root over omega 1 into omega 2. So always these are the very important point, which is omega 1 is equal to minus r by 2l plus under root over r by 2l whole square plus 1 by LC, and omega 2 is equal to r by 2l plus under root over r by 2l whole square plus 1 by LC. So with the help of this we can say these are some of the important formulas. For a series RLC circuit, I have already told you the quality factor is equal to XL by R is equal to X by R. So from this you are going to get the relation of the omega, and if you substitute here we are going to get 1 by R into under root over L by C. Or simply here quality factor is equal to is also a ratio of omega naught by omega 2 minus omega 1. So quality factor is equal to ratio of omega naught by omega 2 minus omega 1. So omega naught is the resonance frequency and omega 2 minus omega 1 is bandwidth. So therefore this is equal to f naught by f2 minus f1. Or simply we can also call it as it's a ratio of the omega naught by the bandwidth. So from this relation we can say these both are inversely proportional. So quality factor is inversely proportional to the bandwidth. And also I've already told you it is equal to ratio of the magnet of the capacitor voltage by the supply voltage, or it is equal to the ratio of the inductive voltage by the overall supply voltage. So this is called as the selectivity of the circuit, or it also called as the quality factor. So quality factor is also called as the selectivity of the circuit. See, I already told you, whenever the omega is going to lie between 0 to omega naught, here the capacitive impedance is very higher than the inductive. So because of that, the circuit is said to be a capacitive circuit or leading power factor. Whereas at omega is equal to omega naught, thus the circuit is purely resistive. So it is also called as a unity power factor circuit. But when when the omega is greater than the omega naught, so therefore we can say simply whenever omega is going to lie between omega to infinity, simply we can say the reactive part is higher than the capacitive part. So because of that, the circuit is said to be a lagging circuit or lagging power factor circuit. And this is the basic relation between the zeta and the quality factor. So zeta is called the damping ratio and Q0 is the quality factor. So this is a very much useful formula. If you know any one, you can figure out the other one. So therefore, zeta is equal to 1 by 2Q. So therefore, zeta is called the damping ratio and Q is the quality factor. So zeta is equal to 1 by 2Q. So you know the quality factor of the series RLC circuit. Substitute that formula, and if you do simplification, we are going to get R by 2 into under root over C by L. So this is the damping ratio of the series RLC circuit. So now we are going to study about the parallel resonance circuit. So parallel RLC resonance circuit. So therefore this is RL, R, JXL and minus JXC. So this is the overall supply voltage of V and the overall supply current of I. So this is IR, IL and IC. So now because these three are in parallel, so overall 1 by Z is equal to 1 by Z1 plus 1 by Z2 plus 1 by Z3. So 1 by Z is Y. So Y is equal to 1 by R plus 1 by JXL plus 1 by minus JXC. So if you substitute XL is equal to omega L and XC is equal to 1 by omega C, and if you do simplification, finally we are going to get Y is equal to 1 by R plus J into omega C minus omega L. But Y is equal to 1 by Z, so if you do the reciprocal of that, we are going to get Z is equal to 1 by R plus J into omega C minus 1 by omega L. So now I am going to draw the phasor diagram at the resonance condition only. So you can see clearly what is going to happen. Then as the three elements are in parallel, so voltage will be same. So therefore I am going to take the voltage as the reference vector. And also you can see clearly that here it is in a resistor the current and the voltage are in same phase. Whereas in the capacitor the current is going to lead, and in the inductor the current is going to lag the supply voltage. But here I am going to take the resonance condition because these two vectors I am going to assume as equal magnitude, means the current in the capacitor and the current in the inductor are same. So because of that, the overall vector in the upward direction is 0. So because of that, the overall supply current is equal to the resistor current. So therefore, whatever the total current should be passed into the resistor itself. So therefore now IR is equal to I. So you can see clearly both are in phase. Then we say this is said to be a resonance condition. So therefore, always this has to be resonance, means the circuit is purely resistive. The circuit is purely resistive when this imaginary part of the impedance or the admittance are 0. So therefore omega naught C is equal to 1 by omega naught at one particular frequency that we are going to call it as a resonant frequency. So if we do simplification, we are going to get omega naught is equal to 1 by under root over LC. So no matter whether series RLC circuit or parallel RLC circuit, always the resonant frequency is same. At that frequency only we are going to get the purely resistive circuit. So therefore now we can say clearly here this is omega naught is equal to 1 by under root over LC. So now Z is equal to R because this part is 0. So therefore 1 by R is called as the R. So Z is equal to R. Whereas Y is equal to reciprocal of this one, we are going to get 1 by R. So this is called as the maximum impedance. In the series RLC circuit, we got the minimum impedance, but we are going to get the maximum impedance. We are going to get the maximum impedance at parallel resonance condition. And the supply current is equal to the current flowing in the resistor. And if you want to know what is the current flowing in the inductor, which is V by XL, but V is called as the IS into, or you can say IR into R, but IR is equal to overall current of I. So I into R by XL, where R by XL is called as the quality factor of the parallel RLC circuit, which is Q into I. Similarly, IC is equal to V by XC, but V is equal to IR into R, but IR is equal to I. So I into R by XA, where R by XA is called as the quality factor of the parallel RLC circuit. So Q into I is again QI. So therefore, IC is equal to IL is equal to Q into I. Where if you want, this is in terms of the radians per second. If you want in terms of the hertz, which is F0 is equal to 1 by 2 pi into under root over LC. So if you are going to draw the graph between the admittance with respect to omega, then we are going to get in this way we are going to get the graph. So you can see clearly here this admittance is decaying up to omega naught, and after that it is going to get increasing in direction. So therefore simply we can say this is increasing but this is decaying. But at omega naught, I've already told you the impedance will be maximum. So you can see clearly here at omega naught the impedance will be maximum. It indicates that you can say the admittance will be minimum. So therefore 1 by R. But at the bandwidth points of cutoff frequencies we are going to get, which is root 2 into 1 by R. So we are going to get root 2 into 1 by R. These are the points we are going to get. See, at omega is equal to omega, the circuit is 2 resistive. So therefore we say it is a unity power factor. But at lesser than omega, what is going to happen is the circuit will be purely inductive circuit. So therefore we can say this is purely inductive circuit. So therefore it will be a lagging power factor. But for omega naught greater than, when the frequency is greater than omega naught, what is going to happen is here the circuit is going to become now leading power factor. It is a reciprocal of the previous series RLC circuit. For series RLC circuit, this is leading and this is lagging. But now they are going to get interchange, which is at less than omega naught the circuit is lagging power factor, and at greater than omega naught the circuit is leading power factor. So I have already told you in the series RLC circuit here it will be leading and here it will be lagging, but in this parallel RLC circuit there will be reversing. So therefore this is lagging and this is leading power factor, but at omega naught still it is a unity power factor circuit. So therefore now if I am going to draw the graph between the magnitude of the current and the omega, we are going to get in this fashion, because at omega naught the impedance is maximum at parallel RLC circuit, so therefore current will be minimum. So like this you are going to get the graph. At this point we are going to call it as I minimum, so it will be root 2 times of the I minimum. So these are the cutoff frequencies, lower cutoff frequency and the higher cutoff frequency. So this is called as the bandwidth. So at these points the power will be means half of the maximum value, or simply we can say it is half of the minimum value, half of the maximum value we are going to get power here. So now the lower cutoff frequency is equal to minus 1 by 2 RC plus under root over 1 by 2 RC whole square plus 1 by LC, and now higher cutoff frequency is equal to 1 by 2 RC plus under root over 1 by 2 RC whole square plus 1 by LC. So the previous one, which is minus R by 2L. So only thing is now we have to replace by here 1 by RC, and everything is same. So therefore here this is the formula that you need to remember. So for series RLC circuit, the omega 1 is equal to minus R by 2L plus under root over R by 2L whole square plus 1 by LC, whereas W2 is equal to minus R by 2L plus R by 2L plus under root over R by 2L whole square plus 1 by LC. That is for the series resistance RLC circuit. But for parallel RLC circuit, which is minus 1 by 2 RC plus 1 by plus under root over 1 by 2 RC whole square plus 1 by LC, whereas omega 2 is equal to plus 2 by RC plus 1 by 2 RC plus under root over 1 by 2 RC whole square plus 1 by LC. So if you want the bandwidth, which is W2 minus W1, and if you do simplification we are going to get finally 1 by RC. So this is in terms of radians per second, but if you want in terms of hertz, which is F2 minus F1 is equal to 1 by 2 by RC, this is in terms of the hertz. So always, no matter whether the series resonance or parallel resonance, always the resonant frequency is equal to the geometric mean of the cutoff frequencies, which is W0 is equal to under root over W1 into W2, which is under root over LC. So always quality factor. Now the quality factor of the parallel RLC is the reverse of the series RLC. So therefore R by XL is equal to R by XC is equal to R into under root over C by L you are going to get. But this is the standard formula, which is it is the ratio of the resonant frequency by the bandwidth, which is W0 by W2 minus W1 is equal to F0 by F2 minus F1. And now I will discuss a very important formula, which is here. If W0 is equal to resonant frequency in terms of radians per second, and W2 is the damped frequency in terms of radians per second, and BW is called as the bandwidth in radians per second, then the relation between each and everything, which is W0 square is equal to W2 whole square plus half of the bandwidth whole square. It's a very important formula regarding the relation between the resonant frequency, damped frequency and the bandwidth. All the units are same, which is radians per second. So therefore omega naught whole square is equal to omega d whole square plus half of the bandwidth whole square. So therefore simply we can say W naught whole square plus W d whole square plus bandwidth by 2 whole square. So this is the relation between the resonant frequency and the damped frequency and the bandwidth of a parallel RLC circuit. And I have already told you the relation between the damping ratio and the quality factor for whether series RLC circuit or parallel RLC circuit, which is where zeta is equal to 1 by 2q. So therefore, quality factor of power RLC circuit, if you substitute here and if you do the replacement, if you do simplification, we are going to get 1 by 2 R into under root over L by C. Where zeta is called as the damping ratio. So now we are going to learn some more important concepts. So listen carefully. So this is a suppose this is a circuit in time domain, which is here there is a capacitor and there is a switch is going to get short circuit. So now here because of that there is an inductor and also capacitor. So the capacitor voltage is Vc of t. So these are going to interchange the energy from electrostatic to magnetic and again magnetic to electrostatic. So if you want to convert this circuit diagram into Laplace domain, then this will become 1 by SC and it will become SL and this will become Vc of S and this will become I of S. So 1 by SC, I of S and SL. But there is an initial voltage, or you can say, suppose let me assume there is a initial voltage of V0. So therefore then it is going to become V0 by S. So in this fashion, it is a positive, negative, and here also positive and negative. So like this we have to go for this one. So therefore already here this is called as a plus and this is the minus symbol. So this is V0 by S. So you can analyze the circuit and you can get the value of the expression of I of S in terms of all the components you can easily get. See, analysis is for the circuit. Let me assume before I close the switch, the initial voltage of the capacitor is some V0. So even after closing the switch at initial condition, the voltage cannot change instantaneously. So therefore Vc of 0 plus is also equal to V0. And also here I of 0 minus means I assume that the current in the inductor initially is 0. So therefore even after closing the switch at t is equal to 0 plus it will be again 0 because current in the inductor doesn't change instantaneously and the voltage across the capacitor doesn't change instantaneously. So because of that reason only this is 0 for the current and this is V0 for the capacitor. So therefore omega naught is equal to 1 by under root over LC and the voltage across the capacitor equation, which is it is going to decay in this fashion, which is Vc of t is equal to V0 into cos of omega naught t. So therefore Vc of t is equal to V0 into cos of omega naught t, where V0 is the initial capacitor voltage and omega naught is equal to 1 by under root over LC. And if you want to know the expression of the current, which is V0 into under root over C by L into sine of omega naught t. It's a very important relation. Vc of t is equal to V0 into cos omega naught t, whereas omega naught is equal to 1 by under root over LC, and whereas V0 is called as the initial voltage across the capacitor, and I of t is equal to V0 into under root over C by L into sine of omega naught t, whereas omega naught is equal to 1 by under root over LC, and V0 is called as the initial voltage across the capacitor. So now we are going to analyze this beautiful circuit. So you can see clearly there are two branches of the resistor. Here is RL and this is the L, and this is RC and this is C. So this is called as the resistance in the L branch and this RC is called as the resistance in the C branch. And here let me assume the voltage of V at an angle of 0 degree is going to apply. Then the supply current is I and the current to this branch is I1 and the current to this branch is I2. So now we are going to analyze the circuit in a different manners. So now we are going to do the analysis of this circuit. See, for the first branch, so we can say if you want to know what is the overall impedance, which is 1 by Z equivalent is equal to 1 by Z1 plus 1 by Z2. So 1 by Z equivalent I am going to assume as overall impedance, which is Y is equal to 1 by RL plus JXL plus 1 by RC minus JXC. So if you do the rationalization for each and every term, which is into RL minus JXL by RL minus JXL into here RC plus JXC by RC plus JXC. So if you do that factor and if you do simplification, we are going to get Y is equal to RL minus JXL by RL square plus XL square plus RC plus JXC by RC square plus XL square. And here if you do the simplification of taking the real parts one side and taking the complex parts one side, we are going to get Y is equal to RL by RL square plus XL square plus RC by RC square plus XL square plus J of XC by RC square plus XL square minus XL by RL square plus XL square. So we are going to get the overall admittance of the circuit in terms of the real part and also in the imaginary part. So now we are going to study at that condition when the circuit is at resonance. See, when the circuit is at resonance, what are the things are going to happen? We are going to study only those cases, only those conditions at which the circuit is at resonance. So whenever the circuit is at resonance means the circuit is purely resistive. So therefore the imaginary part of the impedance and the imaginary part of the admittance are purely 0. So therefore for this admittance we have to equate this imaginary part to 0. So therefore XC minus RC square plus XC square minus XL by RL square plus XL square is equal to 0. So therefore now this is equal to 0. See, these two terms are equal only when these two terms are equal only when the condition is here X should be equal to XL and also RC should be equal to RL. At this condition only, this total part should be equal to 0. Otherwise, it will be not equal. So therefore, we can say this overall thing will be equal only when XC is equal to XL and also RC is equal to RL. Then only we can say that this overall part will become 0. So therefore, now this is called as when XC is equal to XL. So XC is equal to 1 by omega C and XL is equal to omega L. So if we do simplification, we are going to get omega naught is equal to 1 by under root over LC. So at omega naught is equal to 1 by under root over LC, we are going to get XC is equal to XL. And also this condition also should be satisfied. Then only we can say that a circuit will be at resonance. So a circuit should be at resonance only at two conditions, which are the XL is equal to XC and RL is equal to RC. At these two conditions only, we are going to get the circuit is at resonance. So now I want to find what is the things are going to happen at resonance condition, which is I want to find what is the current in the first branch, which is I1 is equal to V at an angle of 0 by RL plus JXL. So now I am going to convert this denominator into the polar format, the magnitude and also angle. So finally I am going to get V by under root over RL square plus XL square at an angle of minus tan inverse of XL by RL. So this is called as the magnitude of I1 at an angle of minus theta 1. Similarly, I want to find what is the current in the second branch. I2 is equal to V at an angle of 0 by RC plus RC minus JXC. So I am going to convert this into polar format. So finally I am going to get V by under root over RC square plus X square at an angle of plus of tan inverse of XC by RC. I am going to assume this as a magnitude of the current I2 into at an angle of theta 2. So we have got the expression of the I1 and the expression of I2. I have already told you XL should be equal to XC and RL should be equal to RC. So therefore at resonance, so definitely we can say the magnitude of the currents are equal. The magnitude of the currents are equal. And also here XL is equal to XC and RL is equal to RC. So therefore at this condition also these parts, the angle theta 1 is equal to angle theta 2. So therefore simply we can say here at resonance condition, the condition are XL is equal to XC and also RL is equal to RC. At these two conditions we are going to get the circuit as resonance, and also then the magnitude of the currents in the branch 1 is equal to the magnitude of the current in the branch 2, and also the angle in the branch 1 current and the angle in the branch 2 current are both are also same at the resonance condition. So we are going to get magnitude of the current I1 is equal to the magnitude of the current I2 and theta 1 is equal to theta 2. So in the branch current, so we have taken the V as a voltage phasor, then current I1 is going to lag here and this current is going to lead here. So therefore we can simply say that here this is theta 2 and this is theta 1. So this length is equal to this length and also this angle is equal to this angle. So these are the important points whenever at resonance. So at resonance the condition is XL is equal to XC and also RL is equal to RC. Then the resonant frequency is equal to 1 omega naught is equal to 1 by root over LC, and in this condition the magnitude of the current in the branch 1 and the magnitude of the current in the branch 2 both are equal, and also the angle part magnitude of the angle also for the currents in the branch 1 and the branch 2 are also equal. So these are the things that we are going to get whenever the circuit is at resonance. So now we will discuss another concept in the same problem. Then what are the conditions for current to be in quadrature? Means what is the condition for currents to be in quadrature? Means angle between them is 90 degrees. So therefore angle between the current I1 and current I2, which is theta 1 plus theta 2, is equal to 90 degrees. So what is that condition? Now we are going to see. But theta 1 is equal to tan inverse of XL by RL plus tan inverse of theta 2 is equal to XC by RC is equal to 90 degree. Now here this is the equation we are going to get. So now I am going to apply tan on both sides. So we are going to get tan A plus tan B by 1 minus tan A into tan B is equal to tan 90. So tan 90 is equal to infinity, or we can simply say, or simply we can write 1 by 0. So tan of tan inverse X is equal to X. So by using that property we are going to get XL by RL plus XC by RC by 1 minus XL by RL into XC by RC is equal to 1 by 0. So means the denominator part should be equal to 0. Then only we are going to get this value. So therefore if you do simplification of that, we are going to get RL into RC is equal to XL into XC, where XL is equal to omega L and XC is equal to 1 by omega C. So if you substitute here, we are going to get RL into RC is equal to L by C. So therefore at this condition only we can say that the two currents are quadrature to each other or perpendicular to each other. That is the meaning of this condition. So now we are going to go for the same circuit. Now one more analysis now we are going to study, which is analyzing the circuit when RL is equal to RC is equal to under root over L by C. So what is going to happen for this case now we are going to study, which is RL is equal to RC is equal to under root over L by C. So I am going to have this as R. So what is going to happen now we are going to study. So as R is equal to under root over L by C means then R square is equal to L by C. So R square is equal to L by C. So therefore I can write this, I can multiply omega and divide by omega. I am going to get omega L by omega C, where omega L is equal to XL and 1 by omega C is nothing but XC. So therefore XL into XC. So we are going to get R square is equal to XL into XC. So here also you can see clearly this is R into R is equal to XL into XC. So therefore definitely we can say the currents are quadrature to each other. Here also the currents are quadrature to each other. And also here Y is equal to, I have already told you the general expression of the overall admittance of the circuit, which is R by R square plus XL square plus, but here RL is equal to R and RL is also equal to R. So here RC square by RC square plus XC square and RC square RC is equal to R. So I will replace here also plus G of XC by RC square plus XC square minus XL by RL square plus XL square. So this is a basic general expression. So I have made all the things as equal to R. So therefore, so if you substitute and if you simplification this condition, then you are going to get finally 1 by R. So Y is equal to 1 by R, or we can say Z is equal to R. So we can say the circuit is at resonance. So the circuit is at resonance, and also here the currents are perpendicular to each other. So if you want to know what is the branch current in the first branch, which is V at an angle of 0 by RL plus JXL, but RL is equal to R, so therefore V by under root over R square plus XL square at an angle of minus sin inverse XL by R is equal to, this I am going to assume the magnitude of the current at an angle of minus theta 1. Whereas the current in the branch 2 is equal to V at an angle of 0 by R minus JXC. If you want to convert in terms of polar format, which is V by under root over R square plus XC square at an angle of plus sin inverse of XC by R. So this is magnitude of the current I2 at an angle of plus theta 2. So you can see clearly here this is supply voltage V. The current I1 is going to get lagged by theta 1 and the current I2 is going to lead by at an angle theta 2. So you can see clearly now here this is V by under root over R square plus XL square. This is V by under root over R square plus XC square. So now here this, as XL is not equal to XC, so we can say that these currents are not, the magnitude of the currents are not equal. The magnitude of the currents are not equal. So I want to find what is the angle between these two currents, which is theta 1 plus theta 2 is equal to theta. So now theta 1 is equal to tan inverse of XL by R plus tan inverse of XC by R is equal to theta. So if you apply the tan formula, tan A plus tan B by 1 minus tan B is equal to tan theta, based on that property, if you apply the conditions, we are going to get theta is equal to 90 degree, or we can say they are orthogonal to each other. I have already proved that one. So we have learned that in this concept that the magnitude of the currents are not equal, but here the two currents are perpendicular to each other and the circuit is at resonance condition, because the overall circuit is going to have only resistance, means the circuit is now at resonance condition. So for the same circuit, now we are going to analyze one more thing, which is analyzing the circuit when R is equal to RL and RC is equal to 0. Means I am going to assume the RC is equal to 0 and RL is equal to R. Then what I am going to get? See, in the general expression, admittance, if you substitute these values, we are going to get like this. Y is equal to 1 by R by j omega L plus 1 by minus jXA. So if you do the rationalization of this part, we are going to get R minus j omega L by R square plus omega L square plus j omega C. So if you take the real part one side and if you take the imaginary part for other side, we are going to get this expression we are going to get. Now I want to find what is the circuit is at resonance. At what point we are going to get the resonance? Means the imaginary part of the impedance must be equal to 0. So therefore this part should be equal to 0. So if you substitute here, we are going to get the, at that particular frequency we are going to get the resistance, which is under root over 1 by LC minus R by L whole square. So at this part we are going to get the resonance. So if you substitute this omega naught in this expression, this value will become 0. So if you substitute this point and if you do simplification, finally we are going to get y is equal to R by R square plus omega naught L whole square. So this is the thing we are going to get the admittance at this frequency omega naught. And if you want impedance, means just go for the reciprocal of this one, we are going to get R square plus omega naught L whole square by R. So if you divide this R into two parts, we are going to get R plus omega naught L whole square by R. So if you solve this, if you keep here omega naught here, and if you do simplification, finally we are going to get L by RC we are going to get. So this is called as the overall impedance of the circuit at resonance, which is equal to L by RC. So these are the things which are important of analyzing this circuit at two different conditions we have learned. See, this is the first condition that we have learned for this circuit. See, when the circuit is at resonance means definitely XL is equal to XC and RL is equal to RC. Then only we can say the circuit will be at resonance. So the resonance frequency is equal to 1 by under root over LC. And also I have told you at this condition definitely we can say the magnitude of the currents are also equal and also the angles are also equal. So this is the thing that we have learned here at this condition. The second case we have learned that what is the condition for currents to be 90 degrees. So therefore we learned that here the condition is when RL into RC is equal to L by C, then we can say that the currents are orthogonal to each other, or we can say the perpendicular to each other. We don't know about the magnitude values, only we know that they are orthogonal to each other. But in the other case, at this condition, we have know that the circuit is at resonance and also the magnitude of the currents are not equal. The magnitude of the currents are not equal, but here they are quadrature to each other. All these things also we have learned from this concept. So you can see clearly the circuit is purely impedant, or we can say purely resistive, and also the angle part. Here both are going to be quadrature to each other. That also we have learned. But these magnetic parts are not equal and the angle parts are also not equal. But overall value, if we do the summation of these two things, we are going to get the 90 degree orthogonal. So for this case, we have learned about the overall admittance and also at resonance what is going to happen, what is the overall impedance also we have figured out, and also what is the resonance frequency for this circuit also we have learned. Now we are going to learn about the locus diagram. See, the locus diagram is, suppose the circuit is here, we are going to take a RL circuit. So we can say it is a series RL circuit with a voltage source RMS value of V. So the current is going to flow through this resistor and the inductor is current I. So I want to find what is the value of the current I when the L is going to be variable. So I want to know what is the nature of the current when I am going to vary L from 0 to infinity. So I want to figure out the value of the current I for different values of L. So then the general expression current is equal to voltage by impedance, which is V by R plus JXL. So therefore I am going to convert this rectangular format into polar format. So finally I am going to get V by under root over R square plus XL square with an angle of minus tan inverse X by L. So if I substitute L is equal to 0 in this expression, I am going to get, which is here V by R. So therefore L is equal to 0 means XL is equal to omega into L. So therefore XL is equal to 0. So I will get I is equal to this value we are going to get. So wherever XL is there, just replace XL by 0. We are going to get V by R into at an angle of minus 0 degree. So therefore, if you want to plot this point in a polar format, or you can say this is x-axis and y-axis, the distance is V by R and the point is at an angle of minus 0 degree. So this point is called as the V by R at an angle of minus 0 degree. Suppose if L is equal to infinity, then we can say XL is equal to omega into L. So therefore omega L is equal to infinity, or we can say XL is equal to infinity. So therefore if you substitute here, see anything by infinity is again 0. So therefore this we are going to get 0, and here this is infinity by anything is again infinity. So tan inverse of infinity is 90 degree, but there is a minus sign. So you are going to get minus 90 degree. So therefore if you are going to plot this point on the this x and y coordinate, then we are going to get this is the 0 at an angle of minus 90 degree. So you can see clearly as L increases, XL is also increases. As XL increases, we can say that theta is also going to get increased. So therefore we can say it is going to increase from minus 0 degree, minus 1 degree, minus 2 degree up to minus 90 degree. So therefore we are going to get graph in this format from 0 degree, minus 0 degree, minus 1, minus 2, minus 3 up to minus 90 degree with a decreasing amount of amplitude. So therefore we are going to get a semicircle. So this is called as a current locus. The current locus diagram is a semicircle of diameter is equal to V by R. If you want to know what is the center point of this circle, semicircle, which is V by 2R comma 0 is the center of this semicircle. So this is the thing we are going to get if you are going to vary the L from 0 to infinity. So this is a diagram, basically you are going to get the diagram. So center of this semicircle is equal to V by 2R comma 0 and diameter is equal to V by R, and the locus diagram is a semicircle for this one. So now this is some other circuit. For this circuit also same RL circuit, only thing is here now we are going to vary the R, and then we are going to see what is the nature of the current. When R is varying from 0 to infinity, what is the variation of the current we are going to plot. Then current is equal to voltage by impedance, which is V by R plus JXL. I am going to convert this into polar format, which is V by under root over R square plus XL square at an angle of minus tan inverse XL by R. So when R is equal to 0, if you substitute R is equal to 0 in this expression, we are going to get V by XL at an angle of, see, anything by 0 is infinity, so tan inverse infinity is 90 degrees, so therefore this is a minus sign, so minus 90 degree. So now when you substitute R is equal to 0, we got I is equal to V by L at an angle of minus 90 degree. So if you are going to plot this point on this diagram, you are going to get this is V by L at an angle of minus 90 degree when R is equal to 0. But if you substitute when R is equal to infinity, then anything by infinity is again 0, but anything by infinity is again 0. So therefore this we are going to get basically 0. Tan inverse of 0 is 0 degree. So therefore simply we can say there is a minus sign, so minus 0 degree. So you can see clearly when R is a variable, when R is increasing from 0 to infinity, so this magnitude value goes on decreases. As this magnitude value goes on decreases, and also this is also going to decrease. As this part is decreases, it is also goes on decreases, means from minus 90, minus 89, minus 88 up to like it is goes up to minus 0 degree with the decreasing of amplitude. So therefore this is a diagram you are going to get. So you can see clearly now the diameter is equal to V by XL, and if you want to know what is the center of the semicircle, which is comma V by 2XL, and also this current locus is basically a semicircle. So same thing I have written, center is equal to V comma minus V by 2XL, because it is in the negative y-axis direction. So because of that, this is a minus V by 2XL, and diameter is equal to V by XL, and the locus diagram is basically a semicircle. So suppose there is another circuit for this circuit also we are going to draw the root locus diagram. So now for this circuit now we are going to analyze. Suppose there is a two branches of R1 and R2 and L. So this first branch contains only one resistor of R1, and the second branch contains a so now for the circuit we are going to analyze, which is suppose there is a first branch of R1 and the second branch of R2 and L. So now because we are going to connect these parallel branches to a voltage source of Vs, then it is going to send a current of Is. The current in the branch R1 is I1, and the current in the branch 2, which is I2. So now the source current is equal to I1 plus I2, where I1 is equal to Vs by R1 and I2 is equal to here Vs by R2 plus JXL. But if you want to convert in terms of polar format, finally it is going to become Vs by under root over R2 square plus XL square at an angle of minus tan inverse XL by R2. So for this we are going to draw, see, when R1 is going to vary from 0 to infinity, then what is the nature of the source current we are going to figure out. See, when R1 is going to get changed, when R1 is going to change means this is independent of R1, so we can say that this is a constant value. So therefore this is the magnitude and this is the angle. So this is called as this line is called as the diagram of this point. But here this is a variable, so now we have to draw this one, then we have to add these two things to get the overall Is. So here Vs by R1, when R is equal to 0 we are going to get Vs by 0 is infinity, but when R is equal to infinity we are going to get Vs by infinity is again 0. So therefore we first you have to draw the diagram of this parameter, which is Vs by R1. When R is equal to 0 we are going to get this point, and when R is equal to infinity we are going to get this point. So therefore now you have to shift this to this point. So therefore you can see this is a root locus, this is a diagram, so therefore we have to shift this. Actually the point will be in this, the line will be in this direction, we have to shift it to this so you have to shift this line to this direction, then you are going to get the actual root locus, or you can say actual diagram, locus diagram of this Is. So now this is called as the, see, when R1 is equal to 0, this is the point we are going to get. When R1 is equal to infinity, you are going to get finally this is the point. So therefore this is the called as this is called as the actual locus diagram of the source current Is. But this is called as the locus diagram of the branch current I1 when R1 is changing from 0 to infinity. So you can see it is basically a straight line. Now for this circuit also we are going to analyze. See, there is the extra capacitor we are going to include now, which is R1C, and there is a branch of R2 and L. The only thing is from the previous circuit we have just added an extra capacitor. Then we are going to vary this capacitor from 0 to infinity, and then we are going to see what is the nature of the source current Is. So source current is equal to I1 plus I2, where I1 is equal to Vs by R1 minus JXC, and I2 is equal to Vs by R2 plus JXL. So if you want to convert in terms of the polar format, we are going to get Is is equal to ds by under root over r1 square plus x square at an angle of tan inverse of x by r1, and this we are going to get ds by under root over r2 square plus xl square at an angle of minus tan inverse xl by r2. So you are going to get basically two quantities, but here only c is a variable. If c is a variable means only this part is going to get vary, but this part is a constant value. So therefore this is a constant. Only thing is this is going to get vary. So we have to see what is the diagram we are going to get finally. See, first I am going to draw this part. See, basically this is nothing but a magnitude at an angle of minus 90 minus tan inverse of this angle, so minus theta. So we can say this is called as this line we are going to get a point. This point we are going to call it as a, this is the thing. But when c is equal to infinity, when c is equal to infinity, what is going to happen means when c is equal to infinity, xc is equal to 1 by omega c, so therefore xc will become 0. So when you substitute xc is equal to 0, we are going to get here ds by r1 into here this is 0 by again anything is again 0, so it will become 0. So therefore finally you are going to get ds by r1 at an angle of 0 degree. So if you substitute here, we are going to get, this is the point we are going to get. But when you substitute c is equal to 0, then what is going to happen? Because xc is equal to 1 by omega c, so xc will become infinity. So therefore ds by any infinity value is again 0. And similarly here this is infinity by anything is again 90 degrees, so plus 90 degrees. So we are going to get finally this is plus 90 degree you are going to get. So therefore you can see clearly as c decreasing from infinity to 0, we are going to get an increase of angle. Or simply we can say when c is changing from 0 to infinity, when c is changing from 0 to infinity, we can say that simply the angle is going to get decreased. The angle is going to get decreased, but the magnitude part is goes on increases. This is the thing that we can visualize. So this is the locus diagram of the branch current I1, but we have to shift it up to this point, then we are going to get the overall locus diagram of the source current Is. So we can say clearly this we are going to call it as the locus diagram of the source current Is, whereas this is called as the locus diagram of the branch current I1. So now we are going to study about the single phase AC power measurement. So here suppose there is a how to measure the power consumed by a single phase AC power measurement means I want to find what is the power consumed by this load. I want to figure out. See, in order to this one we are going to keep a EDM or dynamometer. It is going to have basically a current coil and also pressure coil. So with the help of this we can measure the how much amount of power consumed by this load. So let me assume the source voltage is EPC of T, which is equal to the voltage across the pressure coil, and the current in the load is going to pass through the CC, and the current through the load is going to pass through the current coil, which I am going to measure it as the ICC of T. Then let me assume that here it's a lagging load, so therefore VPC of T is the voltage across the load and ICC of T is the current through the load. So I am going to assume the load is a lagging load, so therefore current is going to lag the voltage by an angle of small angle of phi. So therefore phi is the angle between the VPC and the ICC. So now I am going to do the analysis of the circuit, which let me assume VPC of T is equal to Vm sin omega t, as the current is going to get lagging. So I am going to assume which is Im into sin of omega t minus phi. Then we can say the instantaneous power is equal to just do the product of the voltage and current. But if you want to know what is the average power, means in one time period, which is 1 by 2 pi integration of 0 to 2 pi VPC of T into ICC of T into d theta. And if you do this integration over one cycle period, finally we are going to get PR is equal to Vm by root 2 into Im by root 2 into cos phi. So Vm by root 2 is called as the RMS value of the supply voltage, and Im by root 2 is called as the RMS value of the supply current into cos phi. So this much amount of average power is consumed by the load. So therefore VPC is nothing but here RMS value of the supply voltage, and ICC means the RMS value of the supply current.